think I just started recording. Okay, let's start. Welcome everyone to this GigaVision workshop. So I'm Feng Yan from Google Research. Let me first introduce the organizer of this talk. Organizer of this workshop. The first one is like Professor Lu Fang from Tsinghua University. Then the second one is Professor George Babastetias from MIT. Then Professor Eugen Gao from University of Bonn. And also Professor David Brandy from Duke University. And Feng Yan from Google Research. Gordon Guo from Baidu Research. So all the 6 organizers. Then the reason why we want to host this workshop, we want to give answer to these 2 questions. The first question, how can the revolution of imaging technology bring opportunity to challenges for computer vision? This is the first question we want to answer. The second question we want to answer is how can computer vision tasks help with the smart camera to achieve real smart? So to achieve this goal, in this workshop, we host 2 challenges. One is one task is to do a long-term kind of multi-target tracking. Another task is to do a pedestrian trajectory prediction. So these are 2 challenges we have there. We also invited 8 speakers from this field, 3 speakers from this field to give us some talks about this. The first one is Professor Yasser Sheikh from SMU, then Zhilin Yu from NVIDIA Research, Professor Chen Song from Brown University, and then Zhilin Wu from MIT, and Chang Gan from MIT IBM Watson AI Lab, and then Professor Achuta Kazambi from UCLA, and Mei Chen from Microsoft Cloud and AI, and also Yu Zhu from Baidu Research. So here is the schedule of this workshop today. First, we have this welcome and opening remark. After that, we have 8 invited talks. So each talk will be 20 minutes, and then include the Q&A. So after that, we have this GigaVision 2021 Challenge Award kind of session. All the challenge winners will share their algorithms, also their experience. Then after that is closing remarks. Okay, with that, we can go to the first speaker, Professor Yasser Sheikh. Professor, feel free to take it away. Let me stop sharing from my side.
Thank you, Fang, for the invitation. Thank you all for attending. Let me share my slides.
Yeah, I can see it.
You can see it? Excellent. All right. So the topic of my talk today is gigapixel sensing for telepresence. And what is telepresence? Telepresence is an attempt to replace what all of us are doing right now, which is ideally we'd like to be in the same space together, with myself giving a lecture, you're listening, and then others giving a lecture, myself listening, meeting afterwards to chat, discuss, as we do in person. But because of the pandemic, because of distance, we have to settle with VC. So we've been doing some work on trying to replicate as realistically as we possibly can interactions between people, even though they're far away from each other. So here is an example of that. So this is myself wearing a headset, and Danny, someone else in my lab, also wearing a headset. And here's the conversation that we're having. So I'll play this and let you watch.
What can your face do? Can you show us?
Well, I've always hoped you would ask me that question. So I have some pretty good, mouth movement.
How about your eyes? Can you look left, right, up, down? Good.
Yeah, I'm gonna be surprised. Ooh. I think one of my favorites is puffing my cheeks.
The mouthwash commercial.
And rolling my tongue.
That's pretty good, actually.
Yeah.
Good.
So we keep going, but the intent over here is to try to get as realistic and a replication of what I would have been doing in the space with Danny as well. Now, obviously over here, this is just the head. but this is a form of a neural avatar, which we call codec avatars. This uses, rather than looking at the classic graphics rendering techniques, and we use instead this new concept of neural rendering, which we introduced in 2018. And since we've been working on the faces, we've sort of improved the resolution, added hair, eyes, hands, and then finally we've been looking at bodies as well. Now, since these are neural rendering methods, they require data to be sampled sufficiently for them to learn what to do well. And to enable codec avatars, we've built this system called Mugsy. So this is an example of one of the systems that we've built. And here what you see is, this is the same system from a different perspective. There are 171 Ethernet, Giga Ethernet cameras. Each one is 11 megapixels and it captures at 90 frames per second. And you see we've attempted to uniformly sample the space around the person as they're sitting. Now this is a spherical image, so it may seem like it's a semicircle, but this is actually almost a complete sphere. There's just a little narrow entry for you to come in. And so this is an example of the system. As it's being calibrated, it automatically removes the person, and then robot comes in, it picks up a calibration object, and then it moves that calibration object around the space and automatically calibrates all of these cameras and produces the reconstruction. So let's look at what the data looks like. So this is the data that produces, many different views, the top of the head, the back of the head, and each of these has enough resolution to be able to, capture the details of each individual. In addition to the cameras, this system also has 450 lights to be able to span not just the view, but also the expression and the lighting space as well. So that's what we see over here. Every viewpoint, lighting conditions and expressions get captured inside the space. And what that lets us do is reconstruct the person, any expression, any viewpoint, and any lighting. And I'll show you how we do this. Our pipeline first takes this data and reconstructs it using frame-by-frame multi-view reconstruction. We follow that up with high precision tracking. So here you can see these are, this is a mesh on top of the 3D reconstruction, and it's capturing really subtle movement. This is a zoomed in view of the side of the person's face. Then we have annotations of key points, segments, and that lets us, get really fine-grained registration of not just the eyes and pupil, but the teeth, nostrils, all of that business as well. And this adds a lot of robustness to the pipeline. So this is our full pipeline where we reconstruct, detect key points, track faces, and then finally learn the avatar at the very end. Now, the model is such, the network that we learn, thanks to this, gigapixel sensing system, we have the expression codes, like we can vary the expression, we can vary the viewpoint, and we can vary the lighting as well in the environment. And the neural network then has learned enough based on the sensing to be able to guess what the thing would look like. So for the same sequence over here, I fix the expression, I fix the view, and we just changed lighting. And you can see the network produces a nice change of the light. We can do two of them together. So we can change the expression code and the light together. And you see this changes the expression and the lighting through the evaluation of a neural network. And then finally, we can change all three together: the viewpoint, the lighting, and the expression code. Okay, and this is an example of, this is a rendering actually, where you see the background changing and it's illuminating her face as you would expect it to if she was in that space itself. This is work that we published in Instagraph this year. And here's the real-time version of this entire thing put up. This is about a week old. This represents the state of the art in our approach. Jason over here is wearing the headset once again. And here, let's hear him describe what his avatar can do. And you can evaluate the level of realism and relightability we've been able to achieve.
Yeah, welcome to the Codec Avatar 2.0 demo. So let me just explain to you what you're seeing. So what this is a volumetric, reliable representation of my face, hair, shoulders, and neck. And on the headset I'm wearing, there are a few cameras observing my eyes and my mouth, and this allows me to animate my avatar in various ways. I'll just go through a few of them now. For example, I can raise and lower my eyebrows, I can squint, widen my eyes, I can look left, right, around, I can scrunch my nose, I can do various facial motions like jaw motions. Yeah.
So this is a rendering and it's all done in real time. And of course, I'm showing this to you in 2D, but you can actually see it in 3D. And it's a very different experience to actually see the person virtually in front of you, even though you know they're not really there. Now, we're moving towards the rest of the body. Hands are an important aspect to it. And in that same capture system, Mugsy, we can also track the hands to a very high degree of precision as well, even despite occlusions. And this is where the multiple views really help, because you can see things and it's easier to resolve these occlusions when you have this kind of dense sensing of that space. This is another view. Anyone who's done vision knows that contact is very difficult to estimate, and here we're actually estimating that too, using a little bit of physics modeling in here too. Here is a really important aspect, and you can see over here, this is some work we did a couple of years ago in strand reconstruction. So we can reconstruct the hair using the same system. And it's not that it just looks good. We can reconstruct the hair strand by strand accurate in this space as well. So that's for the hands, for the face, for the hair. But we really want to get the full body. We want to get acoustics as well. And for that, we built the Socio-Opticon. This is 253 of the same cameras. And I'll play this video to give you an introduction to it. I should probably move this along as there's a constraint in time, but this is what the actual system looks like at the end. These are microphones in there, things sticking out, and each of the holes here are cameras that we mentioned, and there's some on the ceiling as well. Now, the data that this produces looks like this. It's again a person in this center, but you can see them from every viewpoint and at good resolution too. Now, one of the things I find very interesting about this line of work is, there have been many domes that have been made, starting from Tekao Kanade's dome in 1995 at CMU. But we see in Kyoto, in France, in Germany, in the UK, on the West Coast, in China, in Europe, again in CMU, we've seen these capture systems pop up everywhere around the world. And what's very interesting is most of these groups are continuously active. They're still active almost a decade later. So there's something permanent and important about this area of sensing that we see. I charted this out in terms of numbers of years. So this is years. This is like from 1996 to 2021 where we are. And this is kind of a measure of how much data was being produced. So this is gigabytes per second. The CMU one is right over here. The USC Light Stage is over here in 2011. MPI's Michael Black's group, 2015. The highest one in 2015 was with Microsoft. And when we built Mugsy in 2017, it was a significant jump forward. Here you see red is linear extrapolation, blue is piecewise linear, and green is fitting an exponential to the previous measurements there. And so then Google produced their Light Stage in 2020, which was a big step forward from the previous ones, but still not comparable. And then we upgraded Mugsy last year, and then also upgraded Socio-Opticon for the new version, which is this 250 cameras. As you can see, it's kind of like much greater sensing. And this might shock you, but even now we feel like we're not sensing at enough resolution. Like if you get close to the face and hands, it's not enough. So gigapixel, perhaps terapixel sensing is in fact required to really reach indistinguishable from real. And this is an example of to calibrate the system, we actually, we actually use a robot in there because there's so many cameras and we really need to get to precision. So we have the robot arm moving inside there to calibrate the system automatically as well. We have a full pipeline, just as I had mentioned, for face tracking. And the result is something like this. So you can reconstruct the atom inside 3D. And we've also had our first actual interactions in VR as well. You can see both of them are in VR, and Vasu can see Autumn. This is a real-time rendering, and let's play that for a minute or so.
So Autumn, I hear you're starting a new yoga class. What's that like?
Oh yeah, my new yoga class. So I take some yoga classes, right? And I am really trying to like, so they have the warrior pose, right? Where like they're supposed to like do that thing, right?
Nice.
And I can't get my feet position right ever. Like I don't know where I'm supposed to.
So what you saw over there was on the right, the background, the face, the hands, the body, all of them were animated and rendered in real time in VR. And then the final sort of sensing modality in here is the Sociopticon audio system, which has about 1,700 microphones in there. And what we can do with that is reconstruct the acoustic field in addition to the light field in the space, right? So here you see this is the sound field in the space. And we can actually say for any location in that space, what would a microphone or ear hear in that location? And this is important because immersion is both visual as well as acoustic as well. You use your ears to get a sense of the spatial space too. And I'll play this for you to see how it looks.
This is a construct. It's our loading program. We can load anything from clothing to equipment, weapons, training simulation, anything.
And you see like he snaps his finger and we can actually recover the wave that emanates from his snap of his finger. You can see it's like emanating out. And we can also do like a decomposition of that wave as well. One of the things that interests me about this is that when he snaps his fingers, there's actually one wave that shoots out. There's another one that shoots back towards him, bounces off his chest, and reflects off. And we actually interestingly capture that too. And you can see that here. So you see there's the primary wave that comes out and then a secondary wave that comes out here as well. And that's super exciting. So I'll skip through this. So that's the conclusion of it. These are some of the capture systems we've built. And the core kind of breakthrough that we've seen is to get photorealistic interactions. We have to break the trade-off between computation and realism. And neural networks are an excellent way to break that trade-off, but they are data hungry. And for that, we have to build these large gigapixel scale sensing systems. And once we do that, problems that have been long-standing and difficult in the community have been quick and easier, much easier to solve. So, I sometimes say science emanates from data. Certainly in this case, that's true. And with that, I'll conclude. We have a number of papers if you're interested in reading more about the techniques we've used. And this is my email. I'm happy to answer any questions either over email or right now. Thank you.
Okay. Thanks a lot, Professor Yasashik, for the great talk. Yeah, very impressive work. Any questions from audience?
Hi, can I ask a question?
Yeah, sure. Yeah, go ahead.
Hi, yes, sir. Hi. Nice to see you again. Very impressive work. So I wonder, I wonder, if we want to, for one day, also reconstruct perfectly about the unconstrained scenarios, such as street view or like a non-human centric or non-object centric views. Do you imagine what? Can you let us know what are maybe the challenges that we need to overcome, or what is the path maybe towards that kind of addressing those kind of problems? Yeah.
Sorry, just to be clear, do you mean like non-human objects? Like what do we do about non-human objects? Is that the question?
No, it's also about like a non-object centric, meaning that if I have a street view or if I go outdoor, like where maybe it's difficult to put so many cameras, like can you also, do you have some ideas about like also addressing that kind of scenarios?
So, I mean, I have two kind of thoughts about this. The first one is, I am a big believer in we're not able to exceed significantly the affordance that data provides us. It's hard to exceed that. But if we're talking about scenes, I wonder whether we are in such a kind of data impoverished state. because obviously people are capturing data all the time. The major companies, Google, Apple, any map making service has captured all of these and enriched kind of like quantities. This is an example of one of those things we did with scenes. So this is what you're seeing first is a classic textured 3D reconstruction and textured mesh. If you see, that doesn't have any reflectance. There are all these holes in the space. But when we use one of these neural rendering methods to do the reconstruction, it does quite well, actually. You can see the reflections are captured quite well on the ceiling as well. And this too actually runs fine in a kind of in real time. In fact, I wish I could show all of you what this looks like in VR, because it really feels like you're immersed in that space. It looks fully realistic. So I think these methods can scale to street level views as well. But in my view, I don't think we can escape data unless we use like priors or some structures which will also need to be learned at a very large scale from a lot of data too. So in my view, I don't think there is much purchase to escape data requirements. But it might be an interesting area of research to try to quantify or analyze precisely what sampling rate is needed.
Thank you.
Thanks a lot. Yeah. Any other questions? Okay. If no more questions, let's thank our speaker, Professor Yasser again. Thanks a lot, Professor.
Thank you.
Okay. So, yeah. Our next speaker is Changgan from MIT IBM Ocean AI Lab. So he's not here, so he gave me the video. So let me play the video. Okay.
Excuse me, I think the sound is not coming through. Sorry.
Oh, okay.
I'm sorry, perhaps the author can unmute because we can't hear the sound.
Can you hear now?
Not really.
No, not
okay.
yet.
Okay, so. Let me share again.
rendering, realistic physics, as well as very flexible. So the platform is built on top of the state-of-the-art game development platform Unity. And Unity can handle image rendering and physics for us, and allow us to create a wide range of user cases. So in this talk, I will mainly cover 3 key aspects of the TW platform. First, it's highly flexible and general in design. So TW was designed to accommodate a range of key applications, including multimodal perception, physical scene understanding, and also the robot learning, and also the goal. And with the general goal that we want to enable training each of these domains using a single simulator. And secondly, it supports real-time near photorealistic image rendering as well as the high fidelity audio rendering. And thirdly, the TW has very advanced physics capabilities, allowing both rigid body object, soft body object, clothes, and fluid to interact with. So there are multiple ways we can interact with objects and generating physical realistic behavior. User can affect object directly through the API command or through the embodied AI. We can also support that a human can directly interact with the environment using VR, picking up virtual object using virtual representation of their own hand. First, it will be helpful to look like the TW high-level system architecture. First, I want to give credit to our 2 awesome engineering, Jeremy and Sis. So they both are world-class Unity game designer, and without them, it's really hard to have TW here. So TW simulator is composed of 2 main components. The build and Unity executable TW simulator engine that can be either used in Linux, OS, or Windows. And the build is responsible for image rendering, audio synthesis, and now physical simulation. And the controller is a Python program which communicates with the build and using the TW comprehensive command and control API. So the controller can send command to the build, which executes this command and return data back to the controller, representing the state of the world. And the user can write the controller to suit their need for their user case. And basic Python skills are really the only requirement for using TW successfully. In addition to the build and controller, the platform architecture includes 2 other key components. One is the Amazon, it's the Amazon S3 repository, which are all the 3D object model, scene model, materials as out here. And object environment model can be downloaded as runtime into the build as a sound bundler, which are compressed the binary version of the model data. And secondly, there's also a JSON file that is stored locally that is part of TW install. The database contains all model and other metadata used by TW. And a set of Python library classes handle accessing the data at runtime from the controller. So the TW contains rich API support. Currently, we already have over 200 commands covering tasks like scene setup and manipulation, camera control, object interaction into physics, agent navigation and control. And unlike other available simulation providers, TW controller can send multiple commands per time step, allowing for arbitrary complex simulation behaviors. So using TW, we can either generate large-scale datasets for training deep neural network to generate again real-world image for image recognition, and also we can training and evaluate the physical realistic forward prediction models. And training embodied AI agent that can interact, and we can also use the platform to train embodied AI agent that can interact with the environment, changing object and scene state, like the example shown here. I will also discuss about the main components of this kind of multimodal data simulation functionality. To maximize the control over the image accuracy, we have created a wide range of 3D sites that are highly optimized for the research purpose. This is the basic idea of TW model library. And it also came with audio object model actually also coupled with customer physics and audio material behaviors design that can be realistic and accurately simulate the same object that's physical interact in the real world, including generating physical correct impact sounds. So models are also normalized in the real world scale, given a canonical orientation, and also annotated with properly worn-out synthetic category. And we spend a lot of effort for the high-level photorealistic, and we achieve this through the lighting and writing approach, as well as the high-quality 3D environment and object model from our library. So we're using real-time global illumination. Our lighting model utilizes a single light source representing the sun for dynamic lighting, the type of lighting that causes object to cast shadow in a scene. And for general environmental lighting, we utilize the high dynamic ranging image. This kind of, in short, HDRI image contains more information than standard digital images. So they capture the lighting condition at the real location for a given time of day. Actually, this is a common technique using for the movie generation. Most of the thing in TW is start with some type of environment. So our environment asset also span both indoor, outdoor scenes, including several environments created for high quality scanned photo primary aside. And many environments are designed for maximum variability with large amount of details, both at the object level and surface detail. So any arbitrary viewpoint with the scene will deliver suitable and complex varied background. So environment is then populated with objects from our library of high quality 3D model. So the model can be placed in various ways, ranging from completely procedure based on some algorithm, for example, stacking or random scattering with room bunch. And we can also implement this script, the room arrangement. Basically, researchers can write their own controller to suit the need for their individual scenes. And another key feature for TW is the high impact API that can support the impact sound synthesis. This effort is leading by Professor George McDermott's team. And we can provide a high degree of acoustic rendering fidelity, including full audio spectralization, reliability model that respect the geometry of the interior space. This high impact API using model synthesis to generate plausible and also release impact sound in real time based on the mass and the material of colliding object, as well as the parameter of collision, such as object velocity, angle of impact. Here we have some example to demonstrate both the impact sound synthesis and complex physical behaviors in a photorealistic setting. All right. So second part, I want to introduce the powerful, another powerful perspective of TW is their physics simulation abilities. TW actually using several physics agents to support the physics interaction. The first type of physics interaction is object-to-object interaction. So TW included two separate physics engines with sort of different purpose. The first agent is the Unity basic physics engine, PhysiX, that can handle rigid body physics, including collision between rigid bodies. For example, by applying a forward direction force to the object, it can be made to collide with other objects, as we can see on the left. And or you can apply an upward force on a specific point to tip a dining table to make collide, to make object on the table slide off or roll off. And the second physics engine using TW is NVIDIA Flies. So it's basically using particle-based representation of the underlying model to manage collision between different object types. So on the left, we're using closed simulation to drop a sheet which collided with a rigid body fire hybrid object. On the right, a frigid model is dropped into a pool of water, causing significant displacement or splashing. Dropping objects of different size, mass, or material in the fluid can observe the splashing behavior very differently. So we can leverage this tool to estimate the quantity of the object. So this kind of unified operation can help a machine learning model use both underlying physics and random images to learning a physical and visual representation of work through interaction with object in this physical and photorealistic environment. I want to also mention that the data team recently have also using TW to develop a comprehensive benchmark for training and evaluate physical realistic forward prediction model. This dataset is named GigaVision, and it goes beyond the existing related benchmark, containing a wide range of physical scene trajectory and make extensive use of TW deformable clothes and fluid capabilities, and provide the scene with complex real-world object geometry and the photorealistic texture. Here I list some example of the scene scenario. The second type of physical scene interaction is agent to object, where an embodied agent can interact with the environment, changing scene and object state. So as the first step towards using the type of scene to transfer, TW already can support to import standard URDF robot descriptor file. So this allows users to import their own robot model and control them inside the TW simulation. So existing model in TW including fetch, vector UR file, UR10. So the already can be well fit into TW. And by using the low-level API command that control models rerouting and also the drone drive, a user can also potentially build in some high-level interaction behavior, to support their planning task. And we also recently have developed the humanoid agent that can utilize the range of photorealistic 3D model, allowing the agent to be female, male, or even a child. So TW can directly using the motion capture, collected from the real world, and using this motion capture to simulate, the kind of very realistic photo. There is very realistic human action. And we also have the motion blendering system that can using the same motion capture data, but it can apply either to man, female, child, or even child. So it's quite flexible. We believe this kind of functionality will open up many new opportunities for human-robot collaboration. And the third interaction is to human human to object interaction, means that user can directly interact with scene using the VR capabilities. We currently support the Oculus headset, to interact with objects. As you can see, that this provides a sophisticated object interaction control using user own hand. So when using our library object and their form-fitting collider, this provides a lot of opportunity for complex behavior and object interaction, and also open up opportunity how we can train robot model learning from human demonstration data. In this example that is recently done by the dynamic team, they have shown that using this VR capabilities, they can study that human attention and the machine agent attentions that make a preliminary step to building more human-like machine agent that can learn like a child. And also, in conjunction with many firms from MIT, Stanford, we also recently launched a TW transport challenge. So this is a visual guided task motion planning benchmark towards to do the kind of both photo and physical realistic embodied AI. So the motivation is that currently many embodied AI tasks focus much on the navigation task. And also using some scan images, so the interaction ability is not fully leveraging. So our idea is that whether we can using the high physical and the photo, using both the multimodal simulation and also physics simulation ability on TW, and develop some new tasks that require the agent to interact with the environment and change multiple states in the environment to achieve for long horizon tasks. So for this, transport challenge in the task that agent must take action to move around and train the state of a large number of objects to fulfill complex goal. Concretely, that embodied agent here is a micro robot is born randomly in a simulated physical home environment. He must collect a small amount of objects scattered around the house and transport them to the special location. We also position around the house that some container that can be used as a tool to assess that kind of object more efficiently. And the agent must plan optimal path to transport the object to the goal location and reason what the container use. And also concurrent work, there's several well-known researchers from computer vision and robot community also propose some rearrangement tasks as a potential test bed. And our work actually provides a concrete example what the rearrangement will look like in both photo and physical realistic embodied environment powered by TW. We develop physics-driven high-level action, and also we also have the rich sensor data. Agent can leveraging, and also the agent have many channels synchronized navigation, interaction, also the physical aware interaction and navigation. So many interesting perspective has been incorporated, and another so here is an example of what this task look like. So basically, a robot agent interact and pick out objects and place them to the goal location. So we believe this simulation will empower researchers to develop more human-like physics-driven robots. Okay, finally, I would like to thank all the collaborators behind the project, and this is probably all my talk. Thank you.
Okay, thanks, Kang again. Unfortunately, Kang is not here today, so we can go to the next talk. Yeah, our next speaker is Zhiding Yu from NVIDIA Research. Zhiding, feel free to take it away.
Okay, thanks. Thanks, Feng. Can everyone see the slides?
Yeah, but it's not in the presentation mode. So can you...
Okay.
That's much better.
Okay, thanks everyone. It's my pleasure to give a presentation here today. The topic will be about learning with imperfect labels and visual data. During the we have a lot of vision, very cool vision applications, but during the deployment of these visual applications, there are two challenges we all often face. One is that the real world data are imperfect. So for example, we can have domain gaps, we can have data set biases, we can have data noise, and all kinds of non-ideal conditions such as long tail, occlusion, clutter, and all these challenges, they cause difficulties to when you deploy AI model. They may not perfectly function in these under these situations. And the second challenge is that nowadays the AI models, especially deep learning transformers, they are very data hungry. But at the same time, the labels are not as scalable as data, and they are not perfect. For example, you might have inexact supervision, you may have incomplete supervision, you may have inaccurate supervision. For example, your label contains a lot of noise, and those in addition, in the real world, the labels and annotations can be versatile. It can be multimodal. It can be in different forms. It can be very sparse, such as the reward from the robot grasping. So all these poses challenges to the algorithms when you want to leverage these supervision and let the model learn very naturally. So in this talk, I will propose two work that are towards addressing these two challenges. The first one is Disco Box, weakly supervised instant segmentation and semantic correspondence from box supervision. So before we delve into the detail of this work, let us first watch a short video. Okay, so you may wonder these high quality instance segmentation masks, are they generated by any instance segmentation models trained on label supervisions? But actually they are not. The whole model is pre-trained on COCO with only box supervisions. And indeed, this is the goal of this work, that can we propose a box supervised box supervised framework that can jointly generate detection, instance segmentation, and also semantic correspondence all at the same time. So we hope by doing this, we believe that the work will have a lot of downstream applications for example, 3D reconstruction and robot grasping and autonomous driving. And here are the, to start with, DiscoBox, the task network of DiscoBox is based on one-stage instance segmentation method, such as YOLAC and Solo V2. But in this method assume that they have the instance level mask labels to supervise the algorithm. And here in our case, we don't have such a kind of supervision. So one of the other work that we also looked into is called the bounding box tightness prior, which contains a multiple instance learning algorithm that can directly supervise the instance level instance segmentation using box supervisions. However, using just bounding box tightness prior does not work as ideal as possible. So that is why we introduce that is why we introduced these mean teacher-based teacher-student framework, where we use exponential moving average to create an augmented version of the teacher, and also use memory banks to store the features. And then once we have the memory bank, we can very easily store those features of ROIs. And as a result, we can very easily get pairwise objects from the same classes. And what we do here is that we propose a structured teacher. Sorry, this one is auto-playing. So we have a structured teacher that can model the pairwise pixel relationships, both within the box and across two boxes from the same category. So this, I will skip the details of the structured teacher. You may refer, for the sake of time, you may refer to details in the paper. But basically, this structured teacher is a teacher defined by Gibbs energy. And this Gibbs energy, upon minimizing the Gibbs energy using mean field and also the differentiable Hungarian, we can actually get a refined version. We can get a refined version of the instance segmentation prediction. And in turn, we can use this structured teacher to guide the student through consistency loss and dense contrastive learning. And this structured teacher will also produce a semantic correspondence between any pairwise boxes. So such as an example given here. So this is basically the high level framework overview of DiscoBox. So I will present some results of DiscoBox. So the first one is we did experiments on the Pascal VOC. So we got a state-of-the-art results using DiscoBox compared with a previous method. And we also did some ablation study where we found that both the consistency loss and dense contrastive learning help the performance to improve consistently. We also did an experiment where we actually try to remove exponential moving average or remove the structuredness in the teacher. And we found that both of them will lead to decreased performance. And especially if you remove the structured part of the teacher, then the performance becomes much worse. So this shows that the structuredness is very important in providing a very good teacher model. And we also did some ablation sensitivity analysis to show that the algorithm is very robust to the different algorithm parameters. And here's also the result. We scaled the results to COCO because a lot of the previous box supervised methods were only on VOC, which is relatively small. So we want to see what is the performance compared to state-of-the-art algorithms on COCO. And actually, our algorithm generates more than 10% of AP higher than previous state of the previous competitive method, the bounding box tightness prior, which I talked just now. And what's very impressive here is that the Disco box, for the first time, there is a box supervised method that can outperform the legendary mask RCN algorithm on COCO. And mask RCN note that it is trained using mask, and Disco box was trained using boxes. So in terms of both the absolute AP and also the speed, Disco box is better than mask RCN. So this really shows that the box supervised method is starting to close the gap to supervised method and starting to become practical, where there is a huge value people want to use this. And finally, like one of our purpose is definitely to benefit the 3D reconstruction community. So that's why we also provided the functionality to provide multi-object semantic correspondence. And towards this, we also propose a new data set or a new benchmark on Pascal 3D Plus, where it's not guaranteed that the one image only contains one major object, but there can be multiple objects, and object localization is part of the evaluation of semantic correspondence. Yeah, so we have released the code on NV Labs Disco box, and you're welcome to try this out. The second work that I want to introduce today is transformer. So recently, vision transformer and for semantic segmentation has been very popular. So we also looked into this area and for semantic segmentation. And previously, there are some previous work, for example, the VIT, and also people have been using the VIT for semantic segmentation already. But one of the problem with the previous models of VIT is that it is not a pyramid structure. So like it's a straightforward trunk. And this obviously is not very good for dense prediction and also object detection tasks. And so in our case, our work is similar to the pyramid vision transformer, where we have a pyramid structure of a transformer architecture such that the segmentation performance is very good. But of course, there are some challenges. So once you have this pyramid structure, one of the problem is that in self-attention, when you have the complexity of n squared, where n is a length of the sequence. And when you have pyramid structure, the bottom layers are becoming the sequence length is becoming very long. And in order to handle this, we need to propose, we need to overcome these challenges. So so one of the things we did was efficient self-attention, as we show here. But the other thing is that also, a novelty part of this work is we have a positional encoding free design, where this one also benefits the semantic segmentation, because once you remove the positional code, suddenly your training and testing resolution, you can have mismatch and it won't hurt the performance. And we also found that in order to make the network very efficient, it's very important to propose lightweight segmentation decoder. And all these things contributed to the state-of-the-art efficiency versus accuracy performance of segformer, as shown on the figure on the right. So about the efficient self-attention, as I just mentioned, so what we did is that we have a subsampling of the key values. Instead of having the original length of the key value, we actually subsampled by a ratio of R, so that instead of having an O(n) squared complexity, now we have O(n) squared divided by R. So this is why we can afford having a pyramid structure. And then we also propose these positional encoding free design, where what we did is that we found that the 3x3 convolutions actually can leak the positional information in in the transformer. So instead of using positional codes, we can just directly replace all of them with a 3x3 convolution. And this really benefits the segmentation problems. Now you can train on a smaller batch and test on a smaller resolution and test on the bigger patches, and the performance will be still very good. I will skip this part. So one of the things that about the decoder design is that we use a very simple OMLP decoder that basically aggregates the information of all the layers. And interestingly, this design is transformer specific, meaning that it is made possible by inductive biases in transformer. But if you apply the same thing for CNs, it won't work. And the reason, and essentially we observe this, and that's why many current state-of-the-art CN methods, such as DeepLab V3 and other ones, they need to design very heavy decoders. For example, in DeepLab V3, people use ASPP layer to enlarge the basically enlarge these receptive field. So in transformers, we found that this is not necessary. So because at stage 4, the attention of and receptive field of the transformer is already very, very large. So it sees all the context. And that's why a simple MLP or MLP decoder can aggregate both the global information and very local information from the early layers. And finally, as you see, the receptive field, it's a very complementary representation of both local and global representation. That is why the segformer can achieve very good performance. So we did a bunch of ablation studies. Interestingly, we try to make the training crop and the testing crop, the size quite different. And we can see that using the proposed positional encoding free design, the performance is very robust. It doesn't drop much. And we also show that this OMLP decoder design only works for transformer. It doesn't work as well on the ResNets. So that is so these are the ablation studies. We also propose a bunch of models ranging from very lightweight models that can go into the real-time segmentation domain. And for example, our lightest model segformer B0 is faster, performs better than real-time segmentation methods such as ICNet. And then we have heavy model segformer B5, which gives a state-of-the-art performance on both AD20K and cityscapes. Here are some segmentation visualization. What's the most interesting is that we did an experiment on Cityscapes C, which is a corrupted version of the data set. And to show, we found a very robust performance of zero-shot robustness from the transformer architecture. So I will show a demo here. All right. Yeah, we have also made the code of SegFormer available. It is currently very popular on GitHub at NVLabs SegFormer. So you are also very welcome to try them out. So that concludes the today's talk. And thanks very much. And questions are very welcome.
Yes, thanks a lot, Julian, for the great talk. Any questions from audience? Yeah. Then I have a question. So I might miss the last part. Like, why like this transformer is more robust to different kind of distortions? Is that by nature, or like you did some kind of additional work there?
Yes. So I think the transformer. I think this is a very intriguing property, and I need to say we are not the only one who identify this property. There are several concurrent works at NeurIPS. I remember one work also from Google, from Mingxuan. They also identified these intriguing properties, and papers from IBM saying transformers are robust learners. So, but we've been very interesting, and one of the reasons is we believe the self-attention layer, the way it works is. I think it gives a robustness to the vision transformer. The reason is that instead of having local convolutions, which you have a fixed you have a fixed way of learning these representations, the transformers actually the attention will look for similar pixels and similar features. I think when the noise injects the noise, this avoids like getting perturbed, having a lot of perturbed perturbation from the noise. And also in transformers, there are some recent works that, for example, Dino and also several works that shows, okay, some very interesting emerging mid-level representation properties emerge as a result of using the self-attention representation. So for example, because of these long-range dependency, maybe transformers can better capture the context, which help to overcome the corruption in some cases. But I also want to say, attention is not the only reason, it's only part of the reason. We've been also looking into, like, for example, the way the data set augmentation was done during the ImageNet pre-training, and some other. All of these might also influence the performance of vision transformer.
Yeah, thanks a lot, for the great answer. I guess like in the future, maybe like how to attack or defense like a transformer. That's very interesting research topic.
I definitely agree. I remember there is a paper from Alibaba, and already working like transformers are also good at defending attack. But our observation is attacks are more difficult to defend than natural corruptions. That's also our observation. Still very challenging.
Very interesting. Thanks a lot. Yeah. Thanks, Julian, again for the great talk.
Thank you.
Yeah. Thanks. Yeah. Then our next speaker is Professor Achyuta Kadavi from UCLA. Professor, feel free to start.
Great. So thank you so much for having me, and welcome regardless of whatever time zone you're in at this moment. Let me start by sharing my screen. Probably help to have slides. Should hopefully see my screen popping up.
Yep, we can see it. Yeah.
So, inspired by the organizers' kind of initial email to me, I wanted to make this talk more about bridging vision and computational imaging. So we're going to try to bridge those two, and the specifics of what I discuss are not super important. If anyone is interested in getting more into computational imaging, there are a lot of touch points, and feel free to contact me as well. So before I start, a lot of the things that we discussed are really thanks to my amazing students at UCLA. So what's the thesis that we have in our lab? And I think largely in the field of computational imaging, it is that now this may be arrogant, this may be wrong to say, but I believe our best bet of advancing the computer vision problem is through the data that's coming in, and in particular through the information that's coming into the data. So building a better camera, to me, is a really good open space for improving the computer vision problem. So here's one example. This is from Laura Waller, where if you have a lens with a sensor, this is a camera, right? It's like a box with a lens in front of a sensor. And then on the right, you have the human eye here. So this is the camera. And this is the human eye. And so if you look at this example, the eye is not very different than the camera. It's almost the same thing. So if you think about the analogy with airplanes, right? If we want to build something in the air that goes really fast, airplanes don't flap their wings. So for the same reason, why should the camera that's used for computer vision mimic the human eye? And so the computational imaging idea is to co-design everything. So like break all the rules, kind of like break all rules. And think about, first of all, the physics of light. So the physics of light can be multispectral, polarization, thermal, light fields, and so on. Think about generalizing the hardware to something maybe different. So it doesn't need to be a regular camera. And of course, algorithms. And I heard the word inductive bias in the last talk. So you could have an inductive bias from physics as an example, or other types of algorithmic features that are really designed for this types of physics. Now, of course, computational imaging works because, of the terrific advances we've made in deep learning in particular, which have allowed us to approximate any function, right, to an abstraction. So at this point, we can actually start learning very complex physical manifolds. And that makes computational imaging, I think, particularly interesting today. So let me discuss a few pain points you have when doing a computational imaging approach. One of the problems with computational imaging is it's really hard to get started in research, because if you have ImageNet, you have, let's say, 10 million RGB images or more, increasing year on year. And if you want to do, for example, this is a thermal image. You have kind of very few of these images. They're very noisy. They're very small. Both in terms of their size often, as well as their data set size. So there's not many data sets out there. And one of my colleagues, Stefano Soato, likes to often joke around at UCLA that nobody's going to put their cool hyperspectral images online on Flickr or whatever, so you can go and mine them, right? So this is the first pain point. Data sets outside RGB are small, so that makes it hard to do computational imaging. Another pain point is that computational imaging really often relies on the physics of the problem. And the physics of the problem, yeah, they're elegant, they're idealized, but they're not really optically accurate, right? In an unstructured scene outdoors, I cannot go from physical first principles and describe exactly how rain behaves or how snow behaves and so on, okay? So that makes it hard to do computational imaging, because for unstructured computer vision scenes, you require accurate physics. Another pain point is that if you look at deep learning methods, the deep learning methods are not really tuned for physics. Effectively, they have to relearn. Even if you knew the physics, they would have to relearn the physics on their own, because we don't really have that structure in a deep learning network to automatically learn or incorporate or blend physics in general. So ResNet, this is an image, of course, from the famous ResNet paper. I've almost used it without citation because it's so common, but this is from Kai-Ming He's paper, right? In this particular image, one of the origin stories of this, this data is that ResNet was trying to learn a very simple mapping of identity. So it was really tough just to learn an identity mapping. And now oftentimes we're asking networks to learn complex physical mappings, which is not going to work well, right? If networks struggle to learn the identity function. So these are kind of three problems with how the table has been set in computer vision that often makes the bridge between computational imaging and computer vision pretty wide to cross. Now, of course, I'm here to present maybe a solution to this. And I think one solution is to really think about studying deeply the physics of image formation and using that to come to the rescue in three specific areas. The first, and again, this was touched on in the last presentation, is that you can use the physical rules, the ones that you do know, to serve as an inductive bias to machine learning models, okay? And I'll kind of go into that with just an example of polarization. So let's talk about polarization physics. It's not super important that you understand everything about polarization, so I'll break it down to the middle school level. Light is an electromagnetic wave. It has an electric field, magnetic field. Polarization is just the plane that the E field oscillates in. So it's like the rotation of light. So if your red light kind of wave rotates a little bit, you have a different plane of polarization. Where this is interesting is when light gets reflected. So let's say you have light that goes in, hits a surface, and then comes out. The input polarization state here has dots and hashes. And then the output polarization state has only dots, right? So there's kind of like once this light matter interaction happens, this light matter interaction here, once that light matter interaction happens, there's kind of a shift in how the polarization state changes. And so you can describe that behavior with a little bit of physics. So there's a problem called in computer vision, in physics-based vision, called shape from polarization. And the idea is essentially to recover the geometry of an object, the surface normal, using polarization equations. So these specifics don't really matter. I'm not going to go into detail. Basically, it's doing in abstraction what I mentioned in the last slide, which is looking at the input and output polarization, and then figuring out what the surface angle is, using old equations from the 1800s, right? Now, the point I'm trying to make here, so here's the take-home message. Is that there exists some physical closed form solution. Okay. And so now this problem currently lives more in computational imaging or physics-based vision community. So now the question then begs, well, how well does this work? Well, the problem is that it doesn't really work too well on many natural scenes because, so this is kind of take home one, and then there's take home two, is that physics is not perfect. Physics is not perfect. So if you just have this problem live in computational imaging, you're not going to get perfect solutions all the time, particularly when lighting changes or there's some complex effects coming out in the real world that you can't really model with the laws of physics. So the solution then is to use physics, but use it as a form of inductive bias to a neural topology. So combining essentially physics and data. Now, on this slide, there are 5 different ways of solving a physics-based vision problem using a hybrid topology of machine learning and physics. The first one here is obvious. Don't use any physics, just use a naive network, okay? And that's kind of shown here. Maybe a second one that I'll go through here on the slide is a residual physics model, where maybe you have a physical operator like we did on the last slide, that can predict a solution, let's say of surface normals from the input image data. So now you can have a skip connection all the way out to the output, and you kind of add up the solution from physics and a solution from neural networks. And we call this residual physics because the idea is that the neural network, which is shown here, only has the mandate to go and learn what the physical operator cannot predict. Okay, so for example, if I was, just to make it very concrete, if I'm doing trajectory prediction of a tossing ball, so I have a cannon that shoots the ball and it's being tossed, so a trajectory is projectile motion, right? Well, there's going to be air resistance. So physics is going to give you maybe a nice parabola, but due to air,
Hi, Professor Aksan, we cannot hear you. Okay, let's wait a bit. Hey, Professor. Yeah. Oh,
sorry,
okay, now you're back. Welcome back.
Yeah, I think my internet just went down. I'm at home here working from home.
Yeah, no worries. And also, yeah, you have 7 minutes, so maybe like we can be slightly,
Yeah. So I'll be quick.
Okay, thanks.
So you have physical fusion, and so these are other ways to combine physics and data. So we won't go into details here, given the connection drop. And all I will say is that there are ways to optimally blend physics and learning. So here, this is like 5 ways, right, to combine. And then here is kind of a paper where we're looking at maybe what is the optimal way to blend physics. And so very often it reduces down to a fusion architecture. And I'm happy to kind of expand on when you would prefer kind of residual learning versus physical concatenation, feature merging, and so on. So this is a paper from ECCV from one of my students, Yunhao Ba. And he's basically trying to get the shape, the surface normals. And he's doing it by blending physics and learning and getting a much better solution than the previous physics-only approaches. So in the interest of time, feel free to refer to this paper. Okay. So one problem that occurs when trying to blend physics and learning is what happens if we don't know the rules of physics in advance, okay? So maybe we don't have a good abstraction for physics. And so one way of doing this is to discover the laws of physics from video. And here we actually have, this is a video, a GIF image, but I'm on my iPad, so it's not playing. But essentially one of my students is tossing a basketball into the goal. And so this follows that projectile motion that I showed earlier. And so if you put that through an AI engine, you're actually able to go and discover the ground truth physical laws. Okay. One other way that physics is involved with the computational imaging computer vision gap is that you need to understand physics often to deal with synthetic data and close the sim-to-real gap, right? So this is a paper on exploiting geometric persistence in sim-to-real from Alex Wong and Stefano Suato. And essentially what's happening here is that they are using synthetic data and exploiting physics-based consistency in how they render geometry and photometric cues, right? They look at the persistence of certain cues and find that there's an optimal way to essentially learn sparse geometry from synthetic data. The third way that physics of image formation can come to the rescue is also to help with the design of new computational cameras. So if we want to build new forms of computational cameras, one way of doing that is to understand, okay, what types of sensors are important to capture high fidelity data. So here you have a coffee cup and you want to get a 3D model. Of course, you could use deep learning methods or post-processing software or do structure for motion or do time of flight imaging like Kinect, but you end up getting very low resolution images if you do it that way. And very little that you do in computer vision in post-processing is going to be able to improve this result. Another option is to use kind of more expensive hardware, but sometimes even that is difficult. So you can see that this coffee cup has these fine detail, fine grooves. It's very hard to pick up. One of the solutions is to use a computational imaging approach. And if you use computational imaging, you can use polarization of light, for instance, to get the geometry with extremely high fidelity. So this was actually published in ICCV 2015, so some time ago, and we call this polarized 3D. And some of this has been commercialized into a company called Akasha Imaging, okay, which is trying to bridge the computational imaging and computer vision gap by using polarization as well as inductively biased kind of networks. And so this website is at akasha.im. Okay, in case one wants to check it out. All right, so you can see if you were to zoom in on those grooves, you would see that that detail has really been preserved and kind of now you have a very high fidelity model. If you want to read more about physics, we had during the virtual session, we had a tutorial on visual physics. And I think what's important is, of course, you have the recorded talks, which may be of interest, but I think more importantly, there's an active reading list there. And if you have any suggestions for papers that should be added, perhaps even your own, feel free to email and we can get that up there. This is kind of a list of a few of the papers that are on there right now, if you're interested in reading more. I'll kind of close with the fact that we are always welcome to new members in computational imaging. We have ICCP as one of our conferences. There's always the potential to collaborate as well at the intersection of hardware and software. So if any of you have ideas on how you'd like to leverage my lab's hardware or resources, feel free to email me. Also, if you feel like you may be wanting to get into computational imaging, we have a free textbook that was just released a couple of weeks ago. We've made it freely available with a PDF online at this link, imagingtext.github.io. And it kind of goes through computational imaging from first principles. It's a little bit long, maybe like 400 pages or so. But I think if you do end up going through it, I think you'll get a very good, very broad overview of a lot of advances in computational imaging. Okay, so with that, I'm going to kind of end the talk and thank you very much for your attention and sincere apologies for the internet connectivity issue.
No worries. Thanks a lot, Professor Atsuda. Any question from audience? Okay. Yeah, I have a question. I thought like this polarization might be very useful, like dehazing, degree, all this kind of like a vision for different weather kind of like. This is very important for autonomous driving cars. So have you ever like do anything kind of thing on that direction? Or?
Absolutely. So we're actually working on de-weathering kind of papers and projects in our lab. And yeah, physics-based vision, computational imaging, multimodal sensing, very exciting for the bad weather problem. absolutely. So thanks very much for your attention. I think it's 12:30 now, but it was really
yeah, we're just on time. Yeah, thanks a lot, Professor. Okay.
Thank you so much. Really appreciate it.
Thank you. Okay. So, yeah, bye. Yeah, our next speaker is Professor Chen Song from Brown University. Professor Chen, feel free to take it away.
Okay. Can you see my slides?
Yeah, great. Now it's in presentation mode.
Okay, awesome. Thank you for having me. So my name is Chen. I'm a assistant professor at Brown University, and I'm also a part-time research scientist at Google. So I figured that I might be a little bit outlier for this workshop for like computational imaging and video processing, but I'm more like a high-level vision person. And today's talk is a little bit related to this workshop, or it can be a lot related to this workshop in the sense that it's trying to summarize or compress videos, but not, but in a semantic way, right? We are trying to identify the important moments in the video, okay? So the title is called Learning Temporal Dynamics from Unlabeled Videos. And a little bit research about myself. I spent like a few years at Google working with large-scale video understanding. Then more recently, I'm interested in like learning from unlabeled videos, such as learning from narrative videos, cooking videos, to do multimodal visual understanding. And I'm also interested in transferring the learned knowledge from those passive observations, such as videos, to active exploration, such as embodied agents. And a little bit advertisement that I'm looking for like PhD students I will be hiring, and then students who are interested in vision, machine learning, cognitive science, computational neuroscience are all like welcome to apply. Okay, so back to the topic, what can we learn from videos? So this is a frame from a data set we collected 3-4 years ago. It's called Atomic Visual Action Dataset. And it's basically a collection of movies, and we try to annotate things and activities in that. And if you are working on high-level computer vision, you will know that even from this static frame, we can infer we can build machine learning, deep learning models to infer a lot of things, such as what are the objects in this scene, like persons, silverware, food, what are the actions, such as sitting, eating, talking. And then with rich enough annotation, you can do even more complicated stuff, such as the interactions and the near-term future prediction, right? So these are the things that we can hire people to annotate and then train a supervised model on top. And on the other hand, video can be beyond that, right? We can treat video as basically an encyclopedia of multimedia contents, right? Such as from YouTube or from even TikTok. There are a lot of narrated instructional videos where we can learn useful stuff. And it's even beyond videos, right? It can be like illustrated books for the kids or for myself, or Wikipedia. There are a lot of useful multimodal information, such as images paired with captions, right? It's an exciting research area, and it's also one of my research interests lies in. Okay, so if we have such rich encyclopedia of multimodal content, can we be a little more ambitious and ask ourselves, what else can we learn from videos? So one interesting example I personally like a lot is that basically we can collect a lot of passive observations, and that passive observations encode many of the common sense knowledge in terms of pixels or speech or audio, right? For example, if we collect a lot of driving videos, we may build a machine learning model that's able to infer what may happen in the near term in the future, right? And then that's super useful for like planning tasks, because we want to we want the self-driving cars to avoid hitting cyclists or pedestrians, right? So ideally, we want to transfer what we have learned from passive observations, such as videos or like Wikipedia, to like active exploration. So that's the long-term goal. And to approach that task, I'm interested in video understanding, and I'm particularly interested in like learning temporal dynamics. And I like watching cooking videos. So I like to summarize this problem I'm interested in as the egg problem. So basically, I'm interested in learning a function f. That's basically the temporal transitions of objects. And basically, I want to predict what an egg can turn to, right? It can turn into boiled egg, but there's also so many different ways to cook eggs. So the temporal transition model is basically trying to predict the states from a given time t to a future state t plus delta t, conditioned on the original object states, and also conditioned on some actions, right? And the reason why I'm interested in this problem is that it's a more compact representation for videos. You can represent actions as object state transitions. And if you try to solve an inverse problem, then you basically got action recognition. What activities leads to the state transitions? Or object tracking, like if I apply a certain force on certain objects, and then it will turn into another state. And if we recover that state in the future frame, then we can basically identify, okay, those two objects, even though their like states, appearance are different, they belong to the same entity, right? Okay, so the importance of this problem, like it allows us to go towards long form video understanding. Like we can summarize the videos in terms of key moments and do summarization. And it's also a more structured representation organized by objects and their state transitions over time. And I also like to argue like modeling temporal dynamics itself is important. Like for example, for the self-driving car, it's basically if you can predict what will happen in the future, you can use that time dynamics information for planning. So that's the importance of the task, but how? How do people usually do this task? So I think in the earlier days, and for those people who are interested in like video generative models, the answer might be generate future frames, such as earlier work, pioneering work by Carl Wondrich in 2016. I think they built a GAN or VAE, and also by Tianfan in the same year, they built GANs or VAEs to predict the future pictures, right? But the future pictures may be a little bit redundant for what we care about. We care about the states, and then we do not care about the subtleties, like how each pixel would look like. Rather, we want to model the more abstractively, right? And so a more abstract or higher level representation can be visual representations. And indeed, there were previous approach that aims to do that, such as more recently, there were like contrastive predictive coding and a bunch of other temporal sequence generation approaches. And the common assumption they did is that basically they assume the timestamp for the future are fixed, and that itself is an interesting task. But I would like to argue that by assuming that you predict into the fixed amount of future, you are inducing a lot of uncertainty, because in real world, it's actually, you're actually unsure about when the state transition may actually happen, right? So that is another line of work, but it has limitations. So to resolve this sort of uncertainty, there were also other papers trying to, as like exemplified by this paper by Professor Jaya Raman in 2018, right? They tried to predict multiple futures and at different timestamps. And then their loss function is basically, if any of those futures hit the ground truth future, then they say it's a good prediction. And basically that can be implemented by minimization, taking the mean over different predictions. And in that work, they basically apply this for a near future prediction. But again, it's still an open question whether such approaches will be scalable to like predict longer term temporal transitions, such as the egg problem, right? It doesn't, like egg doesn't turn into a scrambled egg within 1 second or 3 seconds, right? So that's the motivation of our work. And so the motivation is that we want to handle realistic future predictions. And we want it to be flexible, right? We don't want to assume a fixed time offset or a limited temporal window. We also want to model the abstract world states. They are high level, right? Such as maybe what we want to describe with a concise language, such as from mix eggs to roll out a doll, okay? And finally, this problem is challenging because it's often unclear for even humans to clearly annotate what will be a correct future state might be, right? So ideally, we want this to be data-driven and unsupervised, and so that we can avoid the manual annotation process. So for this particular example, like this is like pour ice cream, what would be an ideal like time future prediction? So one example, maybe you care about near term, and then you got basically a very similar frame, visual representation. And that might be useful if you are into like modeling local motions or optical flow, but it's not high level enough, right? It doesn't really incur high level state transitions. So that's suboptimal. And you can like predict arbitrarily into the future, like toss a coin and see where it lies. And then that's likely to like retrieve a future that's irrelevant to the starting point. Like in this case, it's like completely irrelevant, right? And the ideal like future prediction is that is what we want to see is that it captures the high level state transitions, such as like cream can be put into an ice cream machine and turn into ice cream. So this is what we want. And how we do it. This is a work done by Dave Epstein, our intern, and Jia Jun and Cordelia Schmidt. Is published at this ICCV. So it's called Learning Temporal Dynamics from Cycles in Narrated Video. So let's take this cooking video as an example. So like we mentioned, we are into multimodal video understanding. So we assume the videos, input videos are narrated, such as we can run automatic speech recognition to get like human speech, and they are also often descriptive of what's going on in the scene. And then basically we are treating those different frames or different like sentences as nodes. And we're trying to build a temporal model that's able to traverse between different modalities and different timestamps. Okay, let's assume that we start from this node, like add soy sauce to the chicken. And then to make, later on, I will talk about the motivation, but we basically rely on the multimodal information to greatly resolve the ambiguity. And to do that, we basically need to first figure out the cross-model correspondence. Let's assume we already trained this model, then it's able to go directly to the relevant text description, which happen to be at the same time, but we do not assume that the correspondent visual and the linguistic information are temporally aligned. And we try to go from the future, right? Predict the future state. And then the key assumption is that if your temporal model is able to predict a meaningful future, basically a temporal a state transition of the same objects, then this process can be reversed in either modality. And then as a result, if we train two temporal dynamics models, one going forward and one going backward, you should be like able to like close the cycle, right? This is basically the cycle consistent laws has been applied for many of the correspondence problems. But here we are using it for like multimodal temporal dynamics recognition. And okay, so I think due to the sake of time, we can see that why this would be helpful, right? From A to B, basically there's no transition in the linguistic space. And then because we enforce our model to like not aware of which modality it starts with, then from A to B is not a good option because we can basically force the model to avoid self loops, right? And from A to C, even if we can go from forward, then you can see that from C to A, there's no way of like tracing that back because you have no information of the cream. And then why would you predict that it would be turned into, it can go back from the cream state, right? It's only from A to D, then D to A that the cycle can be closed. And so this is our model, but the key take-home message is that if we want to commit the cycle with hard selections, then the model is not differentiable. So we implement this with attention mechanism, right? And then everything, all the assignments are solved. Okay, so I'm going to ignore the details, but basically this is the high-level idea, but we need to like apply some heuristics, such as like we want to avoid the boring talking head frames using a so-called concreteness score to filter out the training data, but this is not done during evaluation. Okay, and we also constrain the like self loops. And here are some of the discovered cycles. You can see that we can start from a text description, go to the corresponding visual information that describe the same thing, and then move forward. And for the first example, you can see from you want to rest the dough and then become smoother, right? And then the cycle can be closed. And we can also start from like visual information, go to linguistic, and go forward and go backward. And here are some of the qualitative results. Basically, we can show that our model is able to discover high-level state transitions and without assuming a fixed time offset. And this is exactly what we want. And with this high-level dynamics model, you can do a lot of fun stuff, right? Such as trying to do the temporal ordering, like temporal jigsaw puzzle, given randomly shuffled photo collection, you want to sort them over time, right? And also you can like recognize objects and activities automatically by doing this. Okay, so due to the sake of time, I'm not going to talk about the second work, which is also at SCCV in detail, but the idea is that we want to transfer what we have learned from offline observation, passive observation, such as videos or like text, to embodied agent. And basically we indeed do that. And at the same time, we're trying to build a neural architecture that's able to retrieve relevant information from the past. That's basically the high-level motivation of this task. And in this particular example of visual language navigation, we care mainly about transfer learning in the language space, like trying to understand human instructions in terms and map them into abstract like logic forms. But in the future, and as many other people have explored concurrently, so it would be also interesting to learn grounded visual representations, right? And I think the highlight is that if you are into this like visual language navigation problem, our code is is online, and then there's also pre-trained checkpoints. Okay, as a summary, like there are many interesting tasks for detailed video understanding. I understand there are a lot of like computational photography, image processing tasks as well, but I'm a high-level vision person, so I care about certain things. And it's especially exciting because like you can treat video as one of the encyclopedia of multimedia contents. And we want to learn more things, but for that, I think nowadays everybody agrees we want to do some of the automatic supervision. It can be self-supervised or it can be cross-model supervised. And there are many interesting applications of the detailed video understanding, such as structured multimodal representations for embodied agents. Or another topic I'm really interested in is learning like to build better interpretable, more generalizable models, okay? And finally, I want to thank a lot to my awesome collaborators. And if there are questions, I'm happy to take. Thank you.
Okay. Thanks a lot, Professor Chen Song, for the great talk. Any question from audience? Yeah, then I have a question. Yeah, predict the future looks very hard, right? So the future have like a multi kind of like a ways, right? So how, when you train it, how do you get the data and so you do it more like a unsupervised way, right? So how do you get the data like and also like when you have so many if you just predict the cooking kind of video, it's much doable than like if you know other kind of actions. So yeah,
I think that's a great question. So I think predicting videos in the wild, future in the wild isn't really doable yet.
Yeah.
But there are a lot of situations where the like temporal dynamic is more structured, such as cooking videos or instructional videos, and also like for self-driving scenarios, and also for like robotics manipulation. If you perform an action, what may lead to, and would that lead to like object state transitions if you pick something up, right? So those are the situations where I think it's good to start as a starting point for future prediction. And I know a lot of researchers are working on that.
Yeah, that's a very interesting kind of future. Yeah, like we know, like we have this butterfly kind of effect, right? So, like you know, like you do something here, like it's very hard to predict. Yeah, okay, cool.
And
yeah, thanks a lot, Professor Chenson.
I think. Do you have a question?
Yeah, thanks a lot. Yeah, I do have a question. Thanks. Nice to meet you, Professor Chenson. Yeah, I have a question regarding the what do you think is the in your mind, like what is the ideal way of like reconstructing like a the reconstruction task regarding the future prediction? Because I personally feel like previous work, like reconstructing at the pixel level or image level might not be an ideal way of doing that. I was thinking about maybe at the object representation level, scene graph level, like you want to match at that level rather than the pixel level. I want to hear what you think. Yeah,
I fully agree. Although I think there is a work called action genome or something like that. It's like trying to do scene graph for human activity videos like charades. I think one potential challenge is that if you do they do like manual annotation, and then it's pretty lossy. Like there are a lot of subtle details such as our facial expressions, right? And then those can be important cues for future prediction, but it's hard to like decide what to include in your scene graph. So I think that might be one challenge. I personally think maybe people talk about clip foundation models a lot. So if you can ask the model like, okay, now given the image, I can describe it using sentence by querying clip. So what may happen next? Can I ask that question? So if I can predict the representation using whatever dynamics model, and then I can decode it back into something we can interpret, such as using some multimodal correspondence models, such as clip. I think that would be great. That would be awesome. Yeah.
I see. Thank you so much.
Okay. Thanks a lot, Professor Chenson again. Okay.
Thank you.
Yeah. Our next speaker is Mei Chen from Microsoft Cloud and AI. With that, Mei, feel free to take it away.
Yeah, thank you. Thank you. Let me see if I can share my screen.
Yeah, we can see you.
Let me know if you can see my screen.
Yeah, I can see it. But it's not okay, not in full screen mode. Okay, great. Yeah. No, it works.
Yeah, thank you so much. Wonderful talks and very relevant. So actually, when I saw the invitation, my direct experience with gigapixel imaging is more relevant to pathology images. The whole slide imaging, where just to enable the pathologists to effectively browse, visualize, and navigate the image is a challenge, let alone to automatically analyze the image. So I've been working for many years collaborating on this kind of topic. However, these are still images. So this title of the workshop is Gigapixel Videography. So I thought I will talk about our video related work, even though it was developed using typical consumer videos. There was no assumption about the resolution. So hopefully some of our insights are still useful for gigapixel videography. So what motivated us to think about this problem is that we are actually, a product group is the Microsoft Cloud and AI group, where we do develop models for customers. And no matter how well you train the model ahead of time and understand the customer scenario, there will always be new classes coming up. And then from the convenience and also cost perspective, customers don't want to retrain the model each time something new comes up. So how to, to be able to quickly have the model generalize to the new classes of a scenario with very few label data is quite a real problem that we need to investigate. So that's what motivated us to look into few shot action recognition. And I think the previous talks already touched some aspects just to kind of explain the terminology a little bit. In this few shot literature, when it's the transfer learning is typically called few shot meta testing. Quickly adapt the model for with very few labeled examples on the novel classes, and a lot of the ways they evaluate such models, the benchmarks, what they call 5-way one-shot or 5-shot episodes. Essentially, the 5-way means there are 5 new novel classes. One shot is 1 example per class, and the 5-shot is 5 examples per class. So those are the terminologies they use. And these are the scenario we start with to investigate this problem. I will talk more about how we extend that for more realistic setting to be useful. So in this case, the testing case is that, in the query, you have only 1 or 5 examples to learn from, to adapt to do the prediction. So the standard action recognition, I think, is pretty clear to this audience that, you train on N classes and you also test on the same N classes. For the few shot action recognition, the data is split into base and novel classes. And the few shot meta training is to pre-train on these base classes in episodes to mimic the episodic few shot meta testing. Because in the meta testing stage, they call that episodic meta testing stage. And so this is the illustration of that, with the different episodes, how to meta train the network so that to fine tune that to be able to handle the novel classes during meta testing. And there has been a lot of work in this area and quite well-known and really good work, such as MeMo and the prototypical networks. However, the limitation is that they still assume large-scale supervision is available. And like the previous speakers also mentioned that that's sometimes not available, sometimes it's simply too costly, and particularly when we work with the real customers, that's a very significant issue. We can easily spend 1 million, still not enough. And also these by using a lot of the so-called off-the-shelf supervised pre-trained models, they also impose a very strong prior in the test and performance. And sometimes the real scenarios are out of distribution, and then that will be quite challenging for the model to perform well. So that's what made us think that there's virtually unlimited unlabeled video data, right? Thanks to all these applications where people voluntarily upload a lot of videos that's at their disposal. So that's what motivated us to pose our question as, can we develop models for few shot action recognition without any supervision during meta training, and to still have respectable performance? And this problem is essentially defined at the intersection of few shot learning, action recognition, and also unsupervised learning. We're not the best at coming up with acronyms, so the acronyms are just describing the approach. So the pipeline, I'll go quickly, given the interest of time, is that it's a first start with this unsupervised pre-training, and then 2 steps along the pipeline that we found particularly effective. One is the unsupervised hard episodes generation, and that really helps the model to learn in the self-supervised manner. And another one is the so-called action appearance aligned meta adaptation, conditioned action learning on the appearance model and with the few shot meta testing. So the first 3 steps are called meta training, and the last is meta testing. I probably won't have time to go through the details of each step. I'll just touch the idea of that. So with the unsupervised pre-training, we use the typical contrastive loss and we generate augmentation for both appearance and action samples, and project that using the MLP, and find the match the prediction using inference to you do this pre-training. And in this stage, you can see that at first, if we just do it this way, the learning is generic. There's no specialization for the downstream few shot tasks. Also, the appearance and action are independent at this stage. There's no interaction between them. And we know that, that is not good enough. So we need to really specialize this episodic meta training for the downstream few shot tasks. So there are two problems we need to tackle. Is that how do we do that without labels? Because we want to, alleviate the burden of supervision, labeling. And also another thing is that how do we really effectively combine the action and the appearance stream? So with the first one, we use these unsupervised hard episodes that I mentioned a little earlier. That's pretty effective. So in this one, it's actually a very simple step. I think many people can already, think of it, is that we use 2D CNN for appearance, 3D CNN for action, and then we pick the augmented videos with the least cosine similarity as the hard episodes, and then use the union of hard episodes from hard examples from both appearance and action, and also add a few randomly selected videos and use that to generate episodes to do this hard episode mining. And the second question is like how to really, effectively associate appearance with action. And that is using this module we developed, we call it A3M. It's appearance, action appearance aligned meta adaptation. And the high level idea of this module is that we have this embedding learned using 2D CNN about appearance, and then the 3D action embedding learned through 3D CNN from the actions from the video spatial temporal sampling, and we use a cross attention to associate them. So there's a kind of a soft association of that. We use from the 2D the frames, we use that as value and key, and use the 3D the action as a query, and use that to condition the action on the appearance. We did experiment with the other way around, but somehow this way seems more effective. That part is a little empirical, and so we use we leverage this memo, the prior work for this episodic meta training using these unlabeled hard episodes. So the hard episodes generated from the previous step now is fed into this action appearance aligned meta adaptation module to further associate action with appearance for downstream tasks. And the last step is few shot meta testing. And here, since for few shot learning, there's only sometimes one, sometimes 5 in the typical setting examples. So we use that to first fine tune on these support samples for the novel class, and then use the query for the testing in this once the A3M module and the classifier are fine tuned on the support samples. So we conducted very extensive experiments and also ablation study. That's all in the paper. I'll highlight the overall performance is that they first compare to all the unsupervised video action recognition state of the art, and including the one that's just published at CVPR this year. And the performance is decisively more superior. And the reason I think is very simple, and it really should be, in that the whole pipeline is specialized for few shot action recognition. So it really should do better. And also this is on both 508 one shot and 508 5 shot benchmarks on all the typical benchmark data sets. And then since we are in a pretty practical mindset in that our customers don't really care what approach, novel or not, SOTA or not, you are taking. Is the performance useful enough, right? Because everyone knows with supervision, the performance is still typically the best. So we also compared with the state of the art supervised few shot action recognition. And these are, again, on the two 5-way 1-shot and 5-way 5-shot benchmarks, and also on all 3 typical benchmark data sets. And you can see that sometimes it even outperforms the supervised methods. Overall, it performs, comparatively well. And HMDB is actually a particularly challenging data set where that is, so-called more temporal. So it's still doing decently well compared to that. And also, since we are thinking about real world usage, you cannot tell customers, right? You cannot have more than 5 novel classes each time. So we also validated on N-way 1-shot unsupervised benchmark, meaning that you can go up to for UCF101, you can go up to 21 novel classes. For Kinetics 100, you can go up to 24 novel classes. That's just how many we have in the test data set, just to see how we do. And CVRL was published in this year's CVPR. So that's the most recent SOTA on unsupervised action recognition. So we definitely considerably outperform their performance. And again, I think the reason is because we specialized the processing pipeline for field shot action recognition. So even in the extreme scenarios, it still performs pretty well. And that's all reported in our paper. You're welcome to look into the details and more of the ablation studies. So I'll talk a couple minutes about the extension from this work, since we need to go beyond papers to make real world impact. So, in the real world, there are some, large scale supervision available, right, for images and even for some, videos to an extent. So why not use that, right? Yeah, so that is also important to leverage anything that's available to achieve the highest performance. So that's, what led us to extend this work further to think about how to still leverage available supervision, and also with unsupervised data can we, do even better. So this is the unsupervised field shot learning for videos. This is still a work in progress, so I won't emphasize too much on the exact steps. So first, what we do is that we pre-train on large labeled image or video data set, right? And that's quite typical. And then we fine tune on these large unlabeled data, just like what we developed for the paper. That's conditioned on labeled video data for using semi-supervision. So here, the idea is that we generate a soft pseudo label for each spatial temporal augmentation of a video using this nearest neighbor cosine similarity with the labeled videos, and then use cross entropy laws to minimize the difference between the soft pseudo labels of the augmentations of the same video. And then optionally, we can still further even fine tune these unlabeled video data, because there will be some available, and then use that to do the fine tuning on the few shot videos for the novel classes. So this one we did try that. We instead of using UCF 101, we used something V2 because the performance on UCF 101 is pretty much saturated. It's already very high. So we validated on Kinetics, HMDB, and something V2, and also show these different kind of configurations to show performance. With the model here, first we tried just less than 50 since it's fast. So with the pre-trained on image and 1K with no fine tuning at all, actually the performance is not too bad. ImageNet is pretty powerful. However, with if we fine tune on unlabeled video data only, that definitely decisively improves the performance by quite a number of percentage points. And if we fine tune with only labeled but disjoint, right, video data for the few shot setting, that of course achieves higher performance because you have supervision. However, if we combine them all, right, using fine tune with both unlabeled video data and also this any labeling that's available, like the labeled disjoint video data, is able to improve performance. So from that we can see that leveraging unlabeled video is still very helpful, even if when you have supervision. And we did extend that to transformer, as everyone know that now transformer is all the rage, and definitely even without fine tune, it outperforms ResNet any of the combinations we tried. So definitely it's more powerful. But with that, the trend still holds. Leveraging unlabeled data in this semi-supervised manner still achieves quite a few percentage higher performance. So that's all what I want to present today. Just to summarize that we have this approach that shows that leveraging large unlabeled videos is quite a viable proxy to supervised pre-training. And the reason it performs better is because it's actually really specialized in mimicking the downstream few shot task for better performance. And also, it can be combined with the label data to achieve even higher performance. That's all. Thank you.
Yeah, great talk. Thanks, May. Any question from audience? Okay, yeah, I have a question. So,
yeah,
yeah. When I look at this is a great work. So, have you ever thought maybe use all this multimodality kind of things, audio or other kind of things for this task? And also sometimes you have a weekly kind of supervised kind of way.
Yeah, exactly. Yeah, exactly. Actually, I have a little more. I kind of cut it because of the interest of time. We did validate also on weekly supervised, particularly on the UCF crime data set. It's quite effective, actually quite useful. And also now we are extending to online detection as well, because also related to some earlier talks that in the real world it needs to work on the cameras, right? So it's real world prediction. And multimodal is definitely a very good point, because oftentimes, particularly for action, the audio is quite indicative and much cheaper and more reliable. That's definitely a good idea. Yeah.
Okay. Yeah. Then let's thank May again. So yeah, our next speaker is Zhiling Wu from MIT. So Zhiling, feel free to take it away.
Hi everyone. Yeah, I will share my screen. Okay.
Okay, yeah, it's in print mode.
Not sure why I couldn't find my mouse, but yeah, I will keep this way.
Okay, yeah, it not work. Yeah, thanks.
Okay, yes. Hi everyone. This is Lin from Professor George Baba's thesis group. I'm working as a postdoc researcher in MIT, and our group is mainly concentrating on embedding physics with machine learning for different kind of computational imaging problems. So for today, I'm going to talk about our recent program, which is related to use neural network to learn how to invert the integrated circuits by embedding the physics knowledge in this process. The aim of this project is to get a high resolution 3D internal structure of the IC chips by speed up the data acquisition and image reconstruction process. So in terms of high resolution, we would like to achieve around 10 nanometer resolution in both X, Y, and Z dimensions, which basically in 3D get an isotropic 10 nanometer resolution. But the image forming process is limited by the diffraction, by scattering, and by different noises. And we would like to get a sample size which roughly around 1 centimeter by 1 centimeter by 100 micrometer. So in theory, we need to get around 10 to 18 voxels in order to get the 10 nanometer isotropic resolution in 3D. So in this way, it will take really long time to do the data acquisition and also long time to do image reconstruction. So in the following slides, I'm going to show how the conventional way, when we get enough data measurements to do the image reconstruction in the conventional approach, how long this whole process will take, and show how we are going to solve this problem by involving this physical forming process and machine learning to do this image reconstruction process. So this is the data measurement acquisition we are going to use to do the data measurements. I will briefly go through this process and make it more relevant to this topic, to this workshop topic. So firstly, we are using X-ray since we would like to get the 3D internal information. So we need to use X-ray to transit the object to see inside. And since we are interested in 10 nanometer resolution, which is hard to get for light-based X-ray, we are using synchrotron X-ray from the Argonne National Laboratory to use very high coherent X-ray and using the FLIR zoom plate to focus the X-ray to the sample and do the point-by-point scan and measure the far-field diffraction patterns at the detector. So in this way, the diffraction patterns will record the light-matter interactions for each point. And in order to get the 3D to do image reconstruction, we also need to rotate the sample and record the image at different angles. So in this way, it will take the tonal scan, which need to rotate the sample from different views, and also need to take the tackle scan, which is point-by-point scan for each rotation angle. So in this way, the overall measurements will be the N view, which is the tomography scan numbers times the N scan, which is for each angle, how many measurements, how many points we need to scan for the sample. So over here, I show the sample size of our experiment is roughly around 100 micrometer by 30 micrometer. And in this case, we take around 350 projection, which is 350 rotation angles. And for each angle, we take around 61K exposures, 61K diffraction patterns. So overall, it is around 12 hours for the data measurements. And when we times the scan times N view, it is also a few thousands, hundreds diffraction patterns we measured. And in order to do reconstruction with so many data measurements, we firstly use previous conventional approach, use two-step to do the topography scan by converting the diffraction pattern in the FLIR domain to the image domain, which takes, I will show the time comparison later. And then when we have the 2D projections for each angle, we do a 3D tomography scan to get the 3D internal objects. And overall, it will firstly for the pedestrian scan reconstruction for each angle, it takes around 8 hours for each angle. And since we are having around 350 angles, and we're using 8 GPU to do the reconstruction, it also takes around 362 hours for the pedestrian, the first step reconstruction. And for the tomography scan, it takes around 6 hours, and overall, it takes around 368 hours for this whole reconstruction process, which is roughly around 15 days to get the 3D internal structure of this IC. So imagine if we would like to do a IC defect, defect inspection or the chip investigation. It takes around 10 days to get a single 100 micrometer times 30 micrometer. It is too long to wait to know if this chip is good or not. So that is why we would like to use machine learning to solve this process. So in order to speed up the whole process and reduce the measurements and speed up the image reconstruction, we need to go back to see how this image forming process. So previously, we assume this object as just a plane. There is no diffraction happening inside the IC chip, which is basically the projection approximation shown over here. But this simple approximation needs a lot of measurements in order to get its internal structure. And also it is simple version about this physical model. That is why we need many measurements to get the whole image reconstruction. So if we go beyond this physical model to really look into how X-ray is interacting with the sample, actually since the IC chip has some thickness, so actually for the IC, the X-ray will interact with the chip layer by layer, and that is when we considering diffraction in this physical forming process. That is what we propose. There is another method called the beam propagation method, involves strong scattering and diffraction in this process. So in this way, when we're considering these layer by layer interactions, we are able to get this 3D structure directly by solving an optimization problem. So that is how we propose this process. So firstly, we would like to use a more complex forward model, more accurate forward model to get a crude approximation of the 3D object. And once we get the approximation, that maybe contains many noise or not very accurate, we would like to use the deep learning to try to learn the paired approximation and ground truths, trying to learn the prior knowledges by involving this H, which is the forward model in this whole process. And after we train the whole network and learn the weights of the deep neural network, then we will test on another sample which never seen by the neural network to see how the results behaves. So firstly, I will briefly go through how our current forward model to get the 3D approximation directly from one angle. So in this way, it will be, previously it takes around 350 rotation angles to get the 3D reconstruction. Now, if we directly reduce to only one rotation angle, that is huge reduction in terms of the measurements. So firstly, I will just briefly go through the beam propagation model. So in this way, we will not treat the IC chip as a single layer object. Instead, we will slice the object into different layers, and we will model the X-ray beam and considering the X-ray interact with each layer of the object, and then use a forward model to propagate the field to next layer. So we will do the layer by layer propagation and then propagate to the detector plane. So in this way, we will have a whole forward model of this image forming process. So our problem will be solving this optimization problem by minimize our modeled measurements with the real measurements. And also for X-ray, it will be very complex compared to only using a single illumination coherent mode. So we are also modeling this partial coherence of X-ray. So which just some physics involves this process. After we get that, so for each angle, we are able to get the 3D approximation, which is pretty cool to use as the initialization for the network input. However, for each angle, since the interaction between X-ray and sample is very weak, so when we do the using this approximate method to get the 3D approximation, actually each layer will be very inaccurate. It contains information about each layer will contain information about other layers. So which basically whole information will be comprised together. So it is hard to, we tried with one angle for now, but it is hard to differentiate the final results. So we are trying to optimize the number of rotation angles we use maybe one is not enough to solve this problem. So we gradually add more rotation angles in this process. And we are trying to find a sweet point that we could reduce the whole measurements, but not decrease the reconstruction quality a lot. So for now, we are finding that using 21 angles will be great to get a very good results, and also reduce the whole measurements by around 16 times, which is also much speed up in terms of the whole measurement process. So over here, I show how we combine the 21 rotation angle or 3D approximate, which basically we will do the 3D object to show the beam propagation model I just proposed, and for each rotation angle, and rotate the object to the central rotation angle and average the results to get the approximate. And then after we get the approximate from the pre-processing method, and we will use previous two-step conventional approach to get the ground truth to train the neural network. And before I go to detail about the neural network structures, it is also important to see how the approximate and ground truth behaves. So firstly, the first row is showing the ground truth for the finer features and coarser features in this IC chip. So as we can see, there are many tiny and large features in this 3D structure. And for the approximate, we could see that all the information are still combined together, but it is already easy to see that features, probably it is mostly the coarser features account more in this image. But all information, since they are compressed together in this approximate, in this 3D approximate, so it also gives us the hint how to design the neural network to solve this problem. So we have tried directly use a 3D unit to do this image reconstruction. But it turns out that since the approximate contains many information, compressed many information together, we need to have a long-range feature extraction network to get its information. When we see each point, it need to extract information from the volume from far field. So we proposed a separable 3D H-horse convolution neural network over here. So firstly, it is very simple encoder-decoder network structure. And we are having a 3D network output or input, since we are doing a 3D image reconstruction process. And we cut the whole the IC into 62 by 62 patches. And for each patch, it will contain 280 layers, which is the real layers contains in this IC chip. As we previously mentioned that in these 280 layers, the information are compressed together. So we need to, instead of using conventional 3x3 convolution filters in the 3D unit, we need to use a long-range feature extraction method to get far field information. So over here, we adopt H-horse convolution filters, which like I showed briefly in introduction over here, like instead of using a 3x3 convolution filter, we use this H-horse convolution by inserting zeros besides each convolution filter components. So in this way, we could control the field of view of the convolution filter without increasing the number of parameters and the amount of computation. So which is pretty helpful in our case. And since we are doing a 3D image reconstruction problem, so we proposed to use this H-horse convolution in pyramid in XY plane, YZ plane, and XZ plane, and in 3D to fully extract the information. And in addition, since Z dimension information, which is layer information, are combined together, it is also important to use a larger iterate rate in Z dimension to extract this Z dimension information fully. And finally, after we use this separable 3D iterate convolution to do the image reconstruction, we test on a IC chip which is different from previous training set, and goes through the whole process, which goes through the pre-processing, use the physical model, the beam propagation model, and use the pre-trained network to get the final reconstruction. So over here, I show the final results in terms of causal feature and final feature. So as we could see, by comparing the reconstruction and ground truth in XY, YZ, and the XZ plane, it shows the features clearly and also shows the interaction, the connection in the Z direction. And also some quantitative performance by comparing with some conventional approach. So just some quantitative comparison and visual comparison. And also here is some comparison with other neural networks. Also by incorporating the physical process as we proposed before. So as we can see, all of them actually behaves pretty well. We believe this comes from by involving the physical process in this process. And also we compared by controlling the different iterate convolution in the Z direction. And as the most important part is related to the whole project aim. It is to speed up the reconstruction and the data acquisition process. So as we can see over here, using the two-step approach, the total time to get the data measurement and do the data reconstruction, it takes around 56 hours to go through the whole process. And using our proposed deep learning-based process, the whole process actually takes half an hour for the whole process. So which is roughly around 120 times speed up for this data acquisition and image reconstruction. So to conclude, this approach is we have learned to invert the IC samples with neural networks and speed up the whole process by 120 times and propose a separable 3D iterate convolution for this 3D image reconstruction process by incorporating the physics knowledge and machine learning process. So yeah, that's it.
Thanks a lot, Zhilin, for the great talk. Any questions, comments from audience? Okay, yeah, if no question, I have a question. Like, so you haven't mentioned which kind of loss function you use here, and also like, do you need to pre-train like your network, or and also like you know, do you have any overfitting or like all this kind of problems there? Or?
So over here we are using NPCC, the negative Pearson correlation coefficients loss function, yeah, which proves pretty good for the image reconstruction process. And for the overfitting, so for now, since we are doing a real problem, we would like to get the IC sample. So our current approach is to get the training for the upper part of the IC and test for the lower part of the IC. So to make sure our reconstruction will be accurate, since we have the upper part as the ground truth, but it will still keep our aim, which is to speed up the reconstruction of the IC in total.
Okay, got it. Thanks a lot. Thanks, Zhilin, again for the great talk. Yeah. Then our next speaker is Yu Zhu from Baidu Research. Yu Zhu, feel free to take it away.
Yeah. Okay. So can you hear me right now?
Yeah, I can hear you. Yeah.
Okay,
but I cannot see the slides yet.
I'm sharing it. Just 1 sec.
Yeah, I can see it. It's not in print. Okay, great.
Okay. Oh, sorry. Okay, so hello everyone. So I'm glad to be here today in this GigaVision workshop on ICCV, and I've learned a lot from the previous talks. So my name is Zhu Yu, and I'm now working as a research scientist at IDL Baidu Research. Now I'm based in Beijing. So before I joined Baidu, I was working at some startups and R&D centers in Bay Area. So currently, my research interests are deep learning frameworks and computer vision algorithms. And today, I would like to share a project we are working on called PedalWeight. So in short, PedalWeight is a set of models and tools for visual transformer techniques. PedalWeight is open sourced and it's developed based on Baidu's deep learning framework, PedalPedal. So this project is not based on some specific research paper, but we are trying to provide a series of easy to use state-of-the-art transformer models, algorithms, and tools for researchers and developers to use transformer technique and try their ideas and maybe start their experiment on vision tasks. Firstly, what is transformer? I see that some previous talks have mentioned transformers, but I still briefly introduce the transformer technique here a little bit. So I myself define the transformer architecture as a type of neural network, which has the following characteristics. So the first one is, it is often an encoder-decoder network structure. Either its encoder or decoder can be used individually as a single model, such as a GPT-3 and the BERT. And the second one is inside this encoder-decoder network, it is often have a self-attention module. It's called a multi-head self-attention, so which is designed to learn the relationships between tokens. Here tokens, I mean, it's are the smallest unit of the input sequence. So the third one is this transformer network usually consists of multiple layers, which are usually a set of self-attention layers, normalization layers, linear layers with activations and some residual connections. So in the right figure, it shows a structure of a standard transformer model. And it was originally designed to handle the sequence data, such as some language translation or some other NLP tasks. So why this transformer is important? I will not cover too many technical details here, but let's see some stats of how transformer models perform on NLP tasks. We have found two famous benchmarks in NLP community, the GLUE and the Super GLUE benchmarks. So both benchmarks have public leaderboard showing the rankings of algorithms with their performance. So we can see that, for example, for the Super GLUE benchmark, all the top 15 algorithms are all based on transformer or BERT architecture. So as we know, BERT is called a bidirectional encoder of transformer. So it is also can be viewed as a transformer-based approach. Therefore, we may say that in recent years, transformer-based deep learning models become dominant, at least in NLP community. And why vision transformer? So more recently, the transformer model have been extended and applied in computer vision tasks, such as image classification and object detection. So we call this type of approach as visual transformer, or VIT. So from the late 2020 till now, visual transformer becomes a hot topic in computer vision research. Let's see some numbers. So we found that the 80% of the top 10 models on ImageNet benchmark now are already based on transformer. And more works have been published in recent top conferences, such as CVPR 2021 and also this ICCV 2021. So we also know that the best paper here this year in ICCV is also a transformer network. It's called Swing Transformer, right? So we can see that there is a clear trend that more powerful network architectures have been designed for vision tasks based on transformer technique. And they have shown a significant improvement in performance comparing to the CNN networks. Specifically, we have checked the top 3 models in computer vision tasks like image classification, object detection, and semantic segmentations. So we see that transformer-based models have achieved all the top 3 ranks in these tasks on the public benchmarks. So here is one takeaway, at least in this major computer vision tasks, we see that visual transformer models have surpassed the CNN model and achieved the current SOTA state-of-the-art performance. Based on the above observation, we started a project 2-3 months ago, aiming at reproducing the state-of-the-art transformer models for computer vision tasks. And we try to provide easy-to-use functions and tools for researchers and developers to start their experiment, to try the models on their tasks, and to design and try their new ideas on the, using the transformer technique. So here is our open source project, PedalWit. And currently we have covered 4 vision tasks. It's image classification, object detection, semantic segmentation, and GAN. So why this project? The reason why we start this project is because we found that no matter what deep learning framework it is, there is no easy to use project in the market right now for users to quickly start their research on visual transformer models. We have done some analysis and compared the pros and cons for several popular repos like TIM and PyTorch and some others. And we found that these popular repos have just started to develop, but now only supported very limited number of visual transformer models and tools. The second one is these repos usually targets on specific vision tasks, but the recent transformer models or papers often designed for not only a single task like image classification, but also they also have several downstream tasks as well. So as a result, we are designing this project and we are working on the following tasks. So the first one is we try to develop and reproduce the easy to use state-of-the-art visual transformer models. This is the core of our project. And the second one is we try to organize related functions and tools for users to easily train the models, either from the scratch or fine tuning from pre-trained model weights. And the third one is that we provide easy to read documentations and tutorials for users to start their project. And last one is we aim to provide low barriers for educationers and practitioners in our project. So in short, PedalWit is designed as a high performance, easy to use platform for researchers and developers to try their ideas and design their visual transformer models. Okay, so what is our current status? So currently, our project just released the first initial version and is actively developing our second release. So until now, we have a small number of contributors from graduate students and some researchers who have contributed over 30 papers from 4 vision tasks. The total number of models in our model zoo is already over 140. So in the right figure, I listed some of the algorithms we have reproduced for image classification. We can see that these are all recent transformer-based models. Besides, we keep optimizing our PedalWit framework and developing several tools and functions for like data processing, model training, multi-GPU learning, and more. So how to use a transformer model in our project? We try to make it as simple as possible. For example, if you want to load a pre-trained weights and use the swing transformer in your code, so after importing related packages, only 4 lines of code is needed. The first step is to load the model config file from the file system. Then we build the model, just 1 line of code. And lastly, we load the pre-trained model weights. Then the Python variable model here is ready to use. And if you want to train the swing transformer using our project, and it's also can be easily done by using by running the training script like like we see here. So all you need to do is to change the file path, right? So, and lastly, we provide the pre-trained model weights which can be downloaded, and all these links are listed in our GitHub repo. So what features do we have? We developed our project based on our Baidu's deep learning framework, PaddlePaddle, and our project is implemented fully in Python with very limited number of dependencies. And our code is fully open sourced on GitHub. So we summarize our paddle weight has the following features. The first one is state of the art. So we try to provide the state-of-the-art transformer models for multiple computer vision tasks. And also we implemented state-of-the-art data processing tools and training method and strategies. And we keep pushing it forward. And second one is it's easy to use. So we design the easy configurations for model variants. And we try to make it a modular design for utility functions and tools which you can easily transfer to your project or your code. And it's pretty low barrier for educators and practitioners. And we support fully documentations and tutorials. And also we try to provide a unified framework for all these models. Third one is it's easy customizable. So we have examples for each model to reproduce the paper's results. And also those model implementations are fully exposed for you to easily customize. Usually it's just one Python file. And the model files can be used independently for quick experiments. So the lastly is high performance. We try to make the model training as fast as possible. And we support popular training tools or schemes like distributed data parallel training, which is very simple to use here. And we also provide some other features like AMP, average mixed precision training, and the users can use this to accelerate the model training by just one line code. Okay, so I think finally, if you're interested in anything related to our project, please feel free to contact. And this is the last slide. And we are still in very early stage, and any comments will be appreciated. So here is the project address and my email information. I think that's all for it. Thank you.
Yeah, thanks a lot, Yizhu, for a great talk. Any questions from audience? Okay, so yeah, if no questions, yeah, let's thank the speaker again. Thanks.
Okay.
Yeah. Okay, then yeah, we go to like the second session of our like workshop. Like another exciting part is like we'll announce like the challenge award. Let me present. Okay. Okay. Can you see my screen? Okay, looks like, yeah, it works, yeah. Yeah, so now let's like announce like the third like GigaVision challenge on ICCV 2021 winner teams. So we have two tasks, right? So like for the first task like long-term kind of multi-target tracking, our first place winner is from Inspire Electronic Information Industry. The others are like Xiaochuan Li, Bao Yufan, Runze Zhang, and the instructor is Rengang Li. The second place winner is from Zhejiang Dahua Technology. The others are like Zhiqiang Wang, Pen Zhang, and Jinchuan Yu. So the instructor is He Qun Zhang. The third place winner is from Inspire Group. So the others are like Han Li, Chen Liu, and Qin Lu Zhang. The instructor is Xiao Bo An. So yeah, we will ask like the first like place winner to share like their experience and talk about their technology. I don't know whether people from this group are here. Could you please let me know if any of the others are here? Okay, if no other here, I also have the video, so I can play the video. Okay, let me option. Let me. Share the video.
This is HSS Library. We won champion in GigaVision tracking competition in ICCV. Thank you for the watching. I will tell the pipeline and some details of my method used in the competition. This report will be divided into 3 parts. First is the introduction. We will introduce the dataset and tasks of the competition, as well as some of our analysis of the data set. After that, we will introduce our detection and tracking algorithms in order. In the past decades, computer vision technologies have witnessed the emergence of smart imaging solutions driven by artificial intelligence algorithms. The recent development of deep learning has radically improved the capacity of computational vision. Unfortunately, how to explore the benefit of high-performance imaging so as to inspire and promote more capable computer vision solutions has not been investigated extensively. This proposed challenge aims to bring the attention of large-scale scene understanding with multi-objects to the computer vision community. Built by faculties of King Hua University. Panda. Simple for gigapixel level, human-centric video dataset is the first dataset for large-scale, long-term, and multi-object visual analysis. Captured by gigapixel cameras, videos on Panda cover scenes with a field of view of 1 kilometer. Each scene may contain a head count in the thousands with over 100 times scale variation. The distribution of the Panda dataset is very extensive, and different persons are very different in size, density, viewing angle, distance, and other dimensions. In addition, during the competition, we found the following problems through analysis. First of all, the image contains a large number of crowded people and obstacles, which greatly affects the accuracy of the detection model. Secondly, due to the larger image pixels, the image has lower resolution in the distance, which will also affect the performance of detection and tracking. Third, crowded people and obstacles will affect the accuracy of tracking, and the false negative of the detection model will also cause ID switch. Fourth, false positives in the background area will also affect the tracking performance. Now I will briefly introduce the detection pipeline we used in the competition. First, I use scaled YOLO v4 for the detection architecture. The current MOP accuracy of this model on the COCO dataset is 64% and does not require a large amount of data for pre-training. We use it as our baseline. Link to the code is under the picture. In addition, in order to adapt to this dataset, we've made adjustments in data sampling and pre-processing. We designed an anchor-based sample screening strategy. For a large scene image, we first randomly collect several persons as anchor points. After that, we use these anchor points as the center to cut out several pictures with fixed sides. and use the person boxes with IOU higher than a certain threshold as the person samples of a picture. Finally, we added a denoising step. We masked the person boxes, which are smaller than the threshold, with gray pixels, aiming to alleviate the loss of marginal samples. Previously, I discovered a bad case. Half-visible people at the edge of the image are difficult to detect. I think it may be a negative impact of the cut logic. So I designed this denoising module to solve this problem. It reduced the false negatives generated during detection inference. Usually, researchers use overlapping sliding windows to predict super large pixels. This leads to three problems. First, missed bounding box is prone to occur at the boundary of the sliding window. Second, missed bounding box is prone to occur in close range areas with large person sizes. Third, the balance between the overlap of the sliding window and the efficiency of the operation. In order to solve the above problems, we propose a detection strategy based on multi-scale pyramids. Through separate prediction and fusion of multiple scales, we have effectively avoided the problem of misdetection. The images of each scale are adjusted on the basis of compatible anchor points and output the results. Finally, we put all the output of all sub-pictures through Soften MS to get the final detections. In the competition, our pyramid uses 5 scales, except for the max scale to directly downsample the whole image. The other scales try to collect square images to ensure that the YOLO model can see as much effective information as possible. In fact, this multi-scale pyramid strategy will introduce false positives to a certain extent. This is reflected in 2 aspects. First, as shown on the left, for small size subimages, there exist some larger persons whose regression of the coordinates is not accurate. This is because for these boxes, their area exceeds YOLO's receptive field. In addition, there exists the opposite problem for large size subimages, as shown in the right. Due to the problem of resolution, large size images cannot guarantee that each pedestrian has enough pixels to predict, especially for pedestrians with arms outstretched. These images need to ensure that their limbs have enough pixels to ensure that they are accurately positioned. Otherwise, the phenomenon shown in the right picture will appear, and the detection box predicted by the big subimage is obviously different from the predicted by smaller ones, resulting in false positives. We solved this problem by limiting the output scale of each subimage, ensuring that each image only produces the most size-fitted anchors. This is the intro of the detection method. Now we start the tracking part. The figure shows a common tracking by detection strategy. The Kalman filter is updated to ensure that each person tracked has the latest feature, and the Hungarian matching strategy is used to match the new frame to the history. But this also causes some problems, which are more important in gigapixel scenes. First, the existing strategy uses weighted track and appearance feature to match the detection boxes. This step will rely on the track prediction accuracy so hard, and and cannot effectively guarantee the spatial rationality of person matching. As shown in Figure 1, there are two female persons in red with very close appearance. When the re-identification model is weak, it is easy to cause the switch of this two persons track, which is very unreasonable in space. Second, this tracking pipeline did not use sufficient information from several previous frames, which requires a better re-identification model. Therefore, we designed a new strategy for this. First, we set a track matching range for each person in the current frame, and the re-identification model is responsible for sorting reasonable tracks within this range. Second, we perform track prediction on all current tracks, and use all of tracks that fall within this range as candidate IDs for re-identification. Third, we use the target box as the query and all the candidate boxes as galleys for matching. The complete tracking process is shown in the figure. In the competition, we used scaled YOLO v4 as the backbone of the detection model, and used the raised nest architecture as re-identification model for training. For re-ID training, we use code base pulled from FastReID. In the process of tracking, we first built a reach tracking library, including image features, track predictions, and track status of several frames before the current frame. When we predict a new frame, we need complete the matching between the track and the detection boxes. For each detection box, we extracted its feature and locations to match the existing tracks. Then, we added this new information for the related track for updating the whole library. But there are still cases worth discussing. The existing tracking strategy based on detection results largely depends on the accuracy of detection. And in the crowded people and other parts, the filter method based on intersection over union score will lead to false negatives, which is unavoidable, as shown in the up picture. Therefore, in order to solve this problem, we have added a compensation step. We added a missing box grounding mechanism after pedestrian matching, tried to assign the terminated pedestrians to hidden people that did not exist in the detection results, and narrowed the scope of this grounding based on the trajectory prediction algorithm. Finally recalled the lost boxes. During the competition, we roughly implemented the grounding algorithm based on the low threshold detection results and the pedestrian re-identification algorithm, and gained something. However, the method I designed in the competition will introduce new false positives, unfortunately. During the competition, I only mitigated this by adjusting the threshold, and I will continue to study this issue in the future. We used this whole tracking strategy to get the champion in the competition with a score of 71.93%. That's it. Everyone is welcome to join our research and discussion, and thank you again for the watching. Thanks.
Okay, thanks a lot for the presentation from group 1. Then let me share so the group. Yeah, our second place winner is from like Zhejiang Dahua Technology. Is there anyone from this group will share the algorithm?
I will show the algorithm and I will do the presentation.
Okay.
Can you hear me?
Let me. Yeah, I can hear you. Feel free to.
Okay. I will show screen. Can everybody see my screen?
Yeah, I can see it. So you have 10 minutes. So. Yeah.
Okay.
Yeah, it works. Thanks.
So I will start from this. Hello everyone. This presentation is about ICCV 2021 workshop GigaVision 1 multi-object tracking rank 2 solution. Firstly, I will introduce ourselves. Advanced Technology, we are a team from Advanced Technology Institute in Zhejiang Dahua Technology. Our advantage, our team have been engaged in research and the application of computer vision algorithms such as detection and tracking for many years. Penta dataset. Gigapixel image has large size. Some people are severely occluded and only their head are visible. High resolution cloud and occlusion are challenged for detection and tracking. Frame rate is very important for data association in multi-object tracking. Low frame rate may lead to fragmentation and ID switch frequently. There are many objects with different scale. Scale imbalance needs detection system be more robust. Framework overview. We use a tracking by detection method. It mainly consists of 3 parts: detection, re-ID, and tracking. For higher accuracy, the detection model and the re-ID model are trained separately. Detection part. Detection part, we use multi-scale overlapping sliding window method, which can generate better results for different scale objects in high resolution. In order to detect as many objects as possible, we trained 2 detection networks. One model is trained by detection data with head and forebody class. Another is trained by tracking data with forebody. Using 2 different detection models can avoid the lab differences between detection and tracking data. Re-ID part. We utilize the fast re-ID library as feature extractor for re-ID test. The re-ID model is based on pre-trained model on ImageNet and fine-tuned on Panda dataset. Tracking part. In tracking part, firstly, track head and forebody simultaneously and match head objects and forebody objects so that they share the same tracking ID. Head information is helpful, especially when the forebody is occluded in cloud sense. Especially in head, the head can be continued to track when the forebody is occluded heavily. Secondly, we build and keep a feature pool for each track letter. Instead of a single feature template, the use of feature pool can solve a variable appearance issue in long-term tracking. Thirdly, a global local aligned feature descriptor is proposed for post-re-ID framework. Feature descriptor contains forebody feature, head part feature, and body below head feature. It can deal with the person occluded by others. Tracking part. Fourthly, we use a robust similarity calculation method in a data association. A robust similarity calculation method contains feature distance, spatial distance, and size distance. Appearance distance is more important to associate cloud and fast-moving objects. We can recover the track letter by appearance similarity when occluded objects reappear. And we use spatial distance to control the matching fields. It reduces the error matching effectively. And a cascade matching method is used in a data association. Cascade matching has 3 levels. Highest level, tracklet with head and forebody. Second level, tracklet with head or body only. Third level, tracklets with similar appearance and motion characteristic. Finally, do some post-process for trajectory prettification. Interpolate boarding box for short-term occlusion. Delete short tracklets, which tend to be unreliable. Use human head to estimate full body with the help of a nearby objects. Implementation details. Detection network test detail. We use 64 dense areas and another 3 size for the all areas. Multi-scale test. The original sliding window image, left and right flip. Scale transformation by 1.2 to 0.6. Remove. The human has a NMS threshold is 0.2 and the others are 0.65. Remove the box near the window boundaries and remove the small box in 3200, 60, 400, and 9600 windows. Post-processing. Remove obvious false positives such as a head box is as big as a body box. In this case, the head box is false positive. Tracking detail. Joint tracking. Head and body are matched separately, and the bounding a pair of head and body according to their location. Trajectory prettification. Short tracklets less than 3 frames were deleted. Inner tracklet implementation is applied on tracklet when the number of lost frame is less than 20. Cross-tracklet implementation is applied when the frame gap of 2 tracklets is less than 4. Here is the ablation study. First, we use the fusion network. It increased 4%. And for the joint tracking, it increased 3%. And for the global local align, it increased 1%. For the future port, it increased 4%. And the last for the trajectory prettification, it increased 3%. And we use all the methods together to get the final score is 0.7% for its implementation. Here's here's all for my representation, and thanks for listening.
Yes, thanks a lot, Group 2 for presentation. Another question from audience. Okay, if no question, let's go to the third winner. Okay, so third place winner from Inspire Group. Anyone from this group want to share?
Hello, everyone.
Okay, so let me stop.
First of all, let me share the screen.
Okay.
Can you see my screen?
Yes. Can I put to presentation mode so it makes bigger? No, it's
okay. Okay, hello everyone. It is my pleasure to give my presentation for ICCV 2021 workshop GigaVision Part 1, Multi-Object Tracking. My name is Li Han. I come from AIoT Laboratory of Inspire Company. Today, my presentation is consisted of 5 parts. First of all, it is an introduction for my team. In the second place, we will analyze the task for the contest. Third, we will introduce our algorithm design. And then next, the algorithm test method will be introduced. And last is a summary for this competition. First of all, it is the team introduction. Our team comes from Inspire. Our team comes from Inspire Cloud Information Technology Limited Company. Our team members are Li Han, Liu Chen, and Zhang Qinlu. Our instructor is An Xiaobo. Our team is working on computer vision research and video analysis. In the second place is the task analysis for the competition. The task in this challenge is long-term multi-object tracking for pedestrians. Given a panda video sequence, participants need to submit the pedestrian trajectory in the video, the pedestrian ID, and the position bounding boxes on each frame. There are 4 major difficulties for this competition. First of all, the resolution of the image is large. In the second, the objects in the image are dense and occluded seriously. The distance of features are close, and which makes matching difficult. Third, there is a big difference between scales and features of close-range and long-range objects. At last, there is a big difference between scales and features of close-range and long-range objects. At last, the FPS of the video sequence is 2. Objects move far between adjacent frames. And first of all, the above figure shows an example of dense objects in the image. It will be difficult to match detected results and track because of density of objects. And the left figure is an example of an object appearing in the long range and close range in the image. The scale and the features of the object in long range are quite different from the ones of the object in the close range, which makes it difficult to match. And the figure on the right is an example of fast moving object, which shows the position information of 2 adjacent frames of a same object. Because the frame rate is low and there is almost no LU between the coordinate of the 2 objects on adjacent frames. And in the third part, the algorithm design of our team will be introduced. The framework of us used for training is YOLO version 5, and the reason for us selecting YOLO version 5 frameworks are, first of all, it performs well on COCO dataset, and the MAP on COCO test dataset can reach 0.544. And in the second, it contains lots of training tricks for object detection. We selected YOLO version 5x6 as a detection model and used the model trained on the COCO dataset as a trained model when training. And because of the larger resolution of the image and the large difference between the object scales of the close range and the long range in the image, and we use the sliding window method to crop the image for training. And each image is cropped with 2 scales of 3000 and 6000. And the overlap for sliding window crop is 0.3. According to LOA, we determine to preserve the boundary objects. LOA means the ratio of intersection area of object bounding box and crop the image to the object area. For example, the ratio of the pupil area to the red box area in the image as shown above, and the LOA calculation formula is shown as follows. The framework of pedestrian real ID training is fast real ID. The reason for us selected fast real ID also it contains lots of tricks for pedestrian real ID. And the model selected for training is the MGN ResNet 50 IBN. And we use the model trained on the ImageNet dataset as a pre-trained model when training. And the object tracking algorithm adopts the idea of deep thought tracking algorithm. At first, detect the objects in the image, and in the second, we crop the sub-image of the detected objects and send them to the reality model for feature extraction. If the detected object matches the track object based on the cosine distance of feature similarity, the tracker would be updated, or a tracker will be initialized. After the full video sequence has been processed, an interpolation algorithm is used to supplement for the missed object. Then we'll introduce our algorithm test method. At first, due to the large image resolution, the object has been detected with sliding window method. In the second, for density and series occlusion of objects in the image, cutout and randomly erased data enhancement have been used when training. Third, because of low frame rate and large object distance between frames, object matching has based on feature similarity and physical distance, and we didn't use the IOU match, which used in deep sort. At last, an interpolation algorithm has been used to supplement the missed detection objects to improve the recovery. And we use the distance between the detection frame and the tracking frame to control the object feature for matching. And when the object is large, the distance threshold is also large, and vice versa. Targets exceeding the distance limited will not be considered in matching. And finally, our team best score was 0.6774. At last is a summary for the contest. These are useful tricks to improve for us in this competition. First, we use a larger and deeper model to detect. And second, we didn't use IOU match to supplement the feature mismatching. And then third, we use an interpolation algorithm to improve the recall rate. And fourth, we use cutout and random erase training trick. And at last, we use a dynamic distance threshold to control during feature matching. And that's all for my today's presentation. Thank you very much.
Yeah, thanks a lot, Han, for the presentation. Any audience from any question from audience? Okay, if no question, let's go to like the award announcement. Okay, let me share the slide. Okay. Yeah, so our like the task 2 for this challenge like pedestrian trajectory prediction. The first place winner from Inspire Electronic Information Industry. So like the others are like Xiaochen Li, Bao Yufan, Runze Zhang. Instructor is Rengang Li. The second place winner is from Inspire Group. The others are Chen Liu, Han Li, Qinlu Zhang. Instructor is Xiaobo An. The third place winner is from WinSense Technology. Others are Nanhai Zhang, Yuanjiang, Fan Zhang, Dongyi. Okay, let's ask the winner to share like their technology. Yeah, the first place winner. We don't have them here, but I will play a video. From their video.
This is HSS Laboratory. We won the competition of pedestrian trajectory prediction using gigapixel video hold in ICCV workshop. Thank you for the watching. I will tell the pipeline and some details of my method used in the competition. I will start the speech from 3 aspects. First is the introduction. We will introduce the general situation of the competition and the characteristics of the data set in this section. In addition, we will also introduce some analysis on this data set. After that, we will tell the least squares method and briefly analyze its feasibility on this data set. Finally, we will tell the displacement prediction network which is used in this project and our whole pipeline. In the past decades, computer vision technologies have witnessed the emergence of smart imaging solutions driven by artificial intelligence algorithms. The recent development of deep learning has radically improved the capacity of computational imaging. Unfortunately, how to explore the benefit of high-performance imaging, so as to inspire and promote more capable computer vision solutions, has not been investigated extensively. This proposed challenge aims to bring the attention of large-scale scene understanding with multi-objects to the computer vision community. Built by faculties of Tsinghua University, gigapixel level human-centric video dataset, in terms as Panda, is the first dataset for large-scale, long-term, and multi-object visual analysis, captured by gigapixel cameras. Videos on Panda cover scenes with a field of view of 1 kilometer. Each scene may contain a head count in the thousands with over 100 times scale variation. The task in this challenge is pedestrian trajectory prediction. Pedestrian trajectory prediction in crowded scenes has attracted significant interest recently, since modeling social interactions between agents and predicting human trajectory in complex environments are highly valuable with a wide range of applications in service bots, intelligent systems, and smart environments. The task in this challenge is pedestrian trajectory prediction. A number of pedestrians are selected in a Panda video sequence, whose trajectories are divided into many segments. Given the short-term trajectory with 9 location in 3 seconds, participants need to predict the trajectory of the pedestrian. In other words, the pedestrian height and position on each future frame for a certain period of time afterwards. In this competition, it is 9 location in 3 seconds. The figure shows the timing and spatial visualization of the test set. More specifically, organizers split 3 different test scenes into 5 disjoint fragments. Each fragment contains 6 seconds and 18 frames of pedestrian data. Participants need to predict the next 9 frames based on the first 9 frames of each pedestrian. You can use other pedestrian trajectories as an aid. We observed that for the test set, the visible part and the unknown part between samples do not overlap in timing. Therefore, even we can use the set of pedestrian trajectories to infer the reachability of each point in space. But it is almost impossible to use the companion relationship between people to assist in prediction. Based on this consideration, we plan to use the simplest trajectory prediction method as the baseline, which is the least square method. The least square method is a mathematical optimization technique. It finds the best function match of the data by minimizing the sum of squares of errors. The least square method can be used to easily obtain unknown data and minimize the sum of squares of errors between the obtained data and the actual data. During the competition, we formulated a simple hypothesis. The trajectories of most pedestrians are presented in a polynomial manner. If acceleration is considered, the position of each person on x and y can be fitted by a quadratic polynomial respectively. Shown in the figure are the visualization effects of the least squares method with different visible lengths and different powers. It is not difficult to observe that the result of linear equation with a short visible distance can predict a more accurate step length, and linear equation with a long distance is more accurate in trajectory direction. The curve predicted by the quadratic equation is relatively smoother, but it also creates the risk of a sudden change in direction. Interestingly, we noticed that the simple least squares method fits very well on this data set. In particular, the fitting result of a linear polynomial with short frame visible unexpectedly exceeds the latest methods such as age and former. We believe that the sparseness in the timing causes this phenomenon. Deep networks need more information to fit the relationship between scene information and pedestrians, and these contents are not sufficient in this data set. However, the shortcomings of the least squares method are also obvious. It cannot reasonably allocate weights among multiple pre-frames. So I designed a simple displacement prediction network to predict the relative displacement of the next frame to get a more accurate position. In other words, compared to mainstream methods, I use relative position as the input and output of the network. I hope that the network can be a compensation for the least squares method and reasonably predict the habits of pedestrians when changing directions, rather than relying solely on high-order polynomials for smoothing. The figure is a schematic illustration of displacement prediction method. We try to calculate the influence of the displacement of several previous frames on the motion of the current frame through the fully connected layer. This is based on an assumption that the motion of the current frame is related to a certain weighted combination of previous motions. In the competition, we combine the results of the two least squares methods and the results of displacement prediction net. The performance of some samples is shown in the figure. The green and red respectively represent the least squares prediction with different invisible frames input, and the blue represents the output of the displacement prediction network. Our algorithm finally achieved a score of 0.9461 on the test set and won this competition. We only used a simple method to achieve this task, but there are still many things that can be explored, such as the mutual influence of different pedestrian trajectories, and the space constraints of the map itself. In the future, we will conduct research in these areas, and we also welcome interested researchers to participate in our community. This is HSS Laboratory. The above is our speech this time. Thank you for watching.
Yeah, thanks a lot for sharing. Then we have a second place winner.没有看到他。Yeah, our second place winner is from the Insta group. Anyone want to share?
Hello.
Okay, so let me stop. Thanks.
Hello, everyone. It is my pleasure to give my presentation for ICCV 2021 workshop, GigaVision Part 2, Trajectory Prediction. My name is Li Han. I come from AIoT Laboratory of Inspur Company. And today my presentation is consisted of 5 parts. First of all, it's an introduction for my team. And in the second, we will analyze for the contest. And the third, we will introduce our algorithm design and our algorithm test method. At last, it's a summary for the competition. First of all, it's a team introduction. Our team comes from Inspur Cloud Information Technology Limited Company. The team member of us are Liu Chen, Li Han, and Zhang Qinlu. Our instructor is An Xiaobo. Our team is working on computer vision research, video analysis, and algorithm design. And in the second place, we will analyze the task for the competition. The task in this challenge is the pedestrian trajectory prediction. A number of pedestrians are selected in the panda video sequence, whose trajectories are divided into many segments. Given the short-term trajectory, participants need to predict the trajectory of the pedestrian ID, and the position on each future frame for a certain period of time afterward. And there are 3 main difficulties in trajectory prediction. First is the interaction between people. The trajectory of a particular pedestrian is affected by the position of other pedestrians in the early work. Each pedestrian has to walk LS team once, which causes a lot of calculation and can't really take into account all pedestrians factors, so the capacity is not large enough. In the second, social acceptability, pedestrian trajectory prediction needs to consider people's social attributes. For example, a couple walked from holding hands. In theory, they could other people could drill through from below, but this obviously don't meet people's requirements for privacy. Third, complexity of trajectory. Obviously, there is more than one solution for pedestrian trajectory prediction. Most of the earlier work is based on methods such as optimizing Euclidean distance, which can only give an average good path selection. The left figure shows the trajectory of all pedestrians in the scene. The starting points and ending points are shown in the figure. The black solid line shows the trajectory of the primary pedestrian to be predicted. It can be seen from the figure that there are stationary and moving pedestrians in a dataset, and the moving pedestrians will be affected by the neighbor people to change the moving direction. In the third part, the algorithm design of our team will be introduced. We have tried the linear method, common filter, LSTM, social LSTM, and social GAN method. East square method uses a function to fit the noise to minimize the sum of square of errors. To observe, the observed value is our multiple size of samples, and the theoretical value is our hypothetical fitting function. The object function is also known as a loss function in machine learning. Our goal is to get the model of the fitting function by minimizing the object function. And the common filter is an algorithm for optimization or estimation of system state by using linear system state equation and system input and output observation data. Since the observation data included the influence of noise and interference in the system, the optimum estimation can also be regarded as a filter process. And the core of common filter is prediction and measurement feedback. And the principle of common filter is shown on the right.
Are you still there? Hey, Han, we cannot hear you. Yeah, let's wait for a moment.
The model of social LSTM is formed. The social GAN uses advanced idea of GAN into the task of pedestrian trajectory prediction. The above figure shows the architecture of the overall generator and discriminator of the social GAN network. Although the LSTM is separated in the figure, the LSTM at the same location is shared with, which is also the same LSTM. And in encoder section, each person's location uses multi-layer full connection embedding as the input of LSTM. Then we will introduce our algorithm test method. And these are methods we use to predict trajectory results from simple to better score. At first, we test data with the linear method. After that, we use a common filter to predict trajectory. Then we train a LSTM model and use LSTM directional and social LSTM to predict. And next, we combine common filter LSTM and social GAN to improve. At last, we train the model with noise argument and combine it with common filter. The above figure and the table shows the score of our models and the model combinations. At last, our best score is 1.0392. At last, we will make a summary for the contest. In the contest, these tricks are useful. First of all, LSTM directional is better than social GAN, and which may be caused by the training hyperparameters. And in the second, adding noise augment during training can improve a score. And in the third, we use 3 models to predict 3 trajectories respectively. At last, common filter can be helped for prediction. And on the other hand, it can be explored how to optimize the prediction performance of the model under the condition of the same size of parameters and to test the training rate for these trajectory models. That's all for my today's presentation. Thank you very much.
Yeah, thanks, Han, for the presentation. Any question from audience? Okay. If no question, let's send like a third one. Share the. Okay. So our third place winner is from WinSense Technology. Anyone from this group want to share?
Okay, here. Can you hear me?
Cool. Yeah, let me stop sharing, and then you can share it. Okay. Feel free to start.
Okay. So, hello everyone. I'm Yuan Jiang from WinSense Technology, and our team wins the 3rd place of the task 2. Today, I'll introduce our solutions to you. And this is our team. Both we are from WinSense Technology, around a startup which focus on the data collection and decision making. And now, let's get to the point. The task 2 is named pedestrian trajectory prediction. So we think the locations should be predicted based on these 3 assumptions. First, a trajectory is spatial temporal consistent. Otherwise, the prediction is impossible. But however, a trajectory has randomness in some level, so it could not be that simple. Also, a trajectory has interaction with environments, so the randomness could be restrained. Based on these assumptions, we treat the task as a sequence prediction problem and used an end-to-end deep learning pipeline to solve it. All we know that data is one of the most important part of the deep learning systems. So we visualize the XY distributions of 6 clips in the training set. And from top left to right bottom is the distribution of X, Y, velocity of X and velocity of Y. The distributions of X and Y varies a lot for different things. So we think the normalization of the input must be a simple but effective trick. And here we show 3 types of normalizations. And you can see that, for example, the distributions of the velocity are relatively stable for different things than the distributions of X and Y. And moreover, we observed that the trajectories are complex, and by visualizing and training the training data, we can split the trajectories into several categories. For example, the following type, where someone follows others, so its trajectory can be predicted based on the trajectory of the leader. And the video below shows the moving of the trajectories in one training clip, which is very complete. So we conclude the second and third keys for this task. We must use a powerful network which has the capability to modeling the complex information. And we should have an interaction model to handle the complex relationships. Let's start from a simplest baseline to prove it. And sequence to sequence is a typical pipeline for the task. It commonly has 3 models: encoder, the interaction model, and the decoder. And here we know LSTM is capable of learning the long-term dependencies. So it has been widely used in the pipeline. And in the beginning, we follow the pipeline except the interaction models. Just simply input the X, Y, Vx, Vy of the first 9 frames to produce the hidden embedding. And the decoder uses the embedding and the output from the last step as the input to recursively produce the predictions step by step. We tested the baseline, it got only 2.6. And then we add the instance normalization to the input. The score boosts to 0.4. But we've also found that data augmentation helps a little. And then we found the model is tend to be overfitting when training. So we remove the teaching scheme in training so that the testing and the training is equivalent. And this helps a lot. The score achieves 0.34. Finally, we add some random noise to the hidden embedding to predict multiple results and changing the backbone to bidirectional GRU. The score ends at 0.337. Note that this is all for the old test data. And after that, the new test data is released and we test our model on it. It's around 1.7. So you can see it's a simple but effective baseline, but don't forget the interaction models. So in the next days, we study on several interaction models to improve the capability of the networks. According to the SOTA papers, we use the grid-based interaction network. It usually takes a local grid around the pedestrian as the input of interaction models. The grid-based models usually focus on their neighborhoods instead of on all the people, which is proved to be more effective. And we test 3 types of the interaction models. First is the occupancy pooling. It inputs the X, Y coordinates of the neighborhoods in the grid to a network with some MLPs and pooling layers to output the relationship embedding. And then the embedding is passed to the decoder in an attention manner. For the second method, we replace it with the directional pooling. The directional pooling uses the relative velocity of each person in the grid. Comparing with the XY coordinates, the velocity can deal with the collisions better. And for the last method, we test the famous social pooling. It captures the entire past history of one neighborhood and represents the relationship information using an extra LSTM layer, which encodes the hidden embedding of the trajectory. It uses not only one frame, but the whole trajectory of the neighborhood, which is proved to be more complementary. And both the relative positions and the relative velocity can be encoded in hidden state vector. Also, to submit the multiple predictions, we just simply combine the three models. And finally, this is the result. You can see the naive baseline achieves 1.68, and after adding the normalization, it's increased to be 1.64. Three interaction models improve the score with 0.4, 0.2, 0.4, and 0.7 respectively. And the combined method achieves 1.49, which is our best result. And finally, give a conclusion. First, LSTM-based sequence-to-sequence pipeline is a simple but effective baseline for the task. And second, input normalization is an elementary pre-processing step. And thirdly, the training and testing consistency is important to avoid overfitting. And first, the relationship or the interaction model is the key to handle the complex trajectories. And that's all my presentations. Thank you.
Yeah, thanks a lot, Yuan, for the presentation.
Thank you.
Yeah. Any questions, comments from audience? Okay. If no questions, I think so this is the last talk for this today's workshop. I think we can close our workshop now. Thanks a lot for all the speakers and the audience for the great presentation. I learned a lot of things. Hopefully everyone can also learn a lot of things during the weekend. Thanks. Okay. See you next year. Bye.